Hello. So good morning all. Hello and welcome to our machine learning workshop on YouTube. My name is Akash and I'm the host today. And first of all, let me introduce to you PHN Technology. PHN Technology and software outsource company. We have started in 2013 and we have successfully completed a decade. And from the last year, we have entered the edtech sector, and from there, we our journey started in edtech sector. So now, coming back to the point. So my name is Akash and I'm your host for this event. Today, we have the pleasure of learning for the machine. Am I audible?
Yeah.
Okay.
Please continue.
Yeah. So we have a pleasure to meet our trainer, Mr. Sushan Moon, who is an expert in machine learning, and he has over 7+ years of experience in this field. And I would like to hand over to Mr. Sushan.
Thank you, Ankit. Let me start with sharing my screen. First of all, I'm audible. Hello, I'm audible.
Yes, are you audible? Yes.
I think right now host has disabled participant screen sharing. Can you enable that for me, please? Hey, hi Ankit. Can you please enable the screen share for me?
Yes, sir. Yes, sir.
Okay, got it. On it, just a second. Share. Let me know once when the screen is visible. So, are my slides visible? Okay, seems like the screen share is working fine. So yeah, welcome guys. Welcome to the session on machine learning and data science with Python. In the next 6 hours, we shall be going right from the basics, answering what is machine learning, covering various machine learning algorithms in topics like classification, regression, clustering, and many more. We shall also be seeing how exploratory data analysis needs to be done, where and when the different statistical matrices are to be used, and other things which are required to survive in the field of data science, right? Yeah. So a bit about myself. I am Sushant, data scientist at AWS India. I'm a computer science graduate and postgraduate from IIT Guwahati and ISI Kolkata, respectively. For a good part of my career, I have been working with Amazon as a data scientist. And before that, I was working in the capacity of data scientist and solution architect in the startups. In total, I have 5 years of experience in industry and 2 years in academia. Right. In short, in this short time, I'm grateful to be able to work with 100+ companies of different sizes and expertise, solving challenges in domains like education, hospitality, banking, health, e-commerce, and many more. There is a slight difference in the where basically the emphasis lies when you are working on real world data sets and the model build using them, right? So without further ado, let's just get started, right? To put our agenda formally, we will see what is machine learning, then move into technical notebooks for each of the different domains of machine learning, basically different types of machine learning challenges and corresponding algorithms to solve them. For each different domain of machine learning, we shall see multiple algorithms, how to use them, and what would be the evaluation criteria for them. We shall also see how to deploy the models and interact with these models which are deployed on the servers. We shall also see what are the topics that you should know before you get into an interview to win the bonus points. Now, when we talk about AI or machine learning or data science, we often use these terms interchangeably, but there is a subtle difference. Artificial intelligence or AI is capacity of the computer to mimic human cognitive functions such as learning and problem solving. Through AI, a computer system uses math and logic to simulate the reasoning that people use to learn from new information and make decisions. Now, even though we are far from achieving that as an goal, industry has been calling the services that they offer, which its customer can directly use in their application to tackle problems like recognition in image, video, trans translations, problems between languages like Google Translate, or a chatbot service like ChatGPT as an AI. All of these have been classified by industry as an AI. Now, coming to machine learning is an application of AI. Basically, it's the subset. Machine learning is a process of using mathematical models of data to help a computer to learn without direct instructions. This enables a computer system to continue learning and improve on its own based on experience. And in this subset, we include algorithms like deep learning, neural networks, decision tree, regression, classification, recommendation, and so on. Now, what most of the students lack is in the field of data science. It's not just encompasses machine learning techniques, but it also has methods that involve data mining in case when data is not readily available. Then it also has data cleaning, basically removing the items or the features which are not needed.
Sorry, just sharing the screen again.
Yes, now it is visible, so.
Yeah, I'm audible now. Yes, you're audible.
Yes,
Yeah.
and screen is also visible properly.
Okay, okay. So I was talking about how students lack in the field of data science. Basically, data science not just encompasses machine learning techniques, but it also has methods which involve data mining when the data sets are not readily available. Then it also has data cleaning, basically removing the items or the features which are not needed. Anything that badly formatted or features which have zero to no relationship with the target variable. After the data clean,
data is clean. Then comes the techniques like feature engineering uh, with the help of business logic. Basically, what makes sense for the business. This is the step where you apply visualization and methods learned in statistics to augment the data that you have to enrich it. All of these is included in data science. But do note, this is not all. Data scientists need to keep reading and learn from the latest research as well. Unless the student have the knowledge about all the techniques, he would not be able to relate or map which technique satisfies the constraints of the business problem that they have encountered. Students also need to have firm grasp on what they can explain and defend their work in simpler terms to non-technical audience. Because not all business stakeholders or owners understand the complex machinery which is underneath. So before I move ahead, let me just take a pause to address any questions if there are any in the chat. Okay, seems like there aren't for now. So
Excuse me, sir.
yeah,
So we will be having a Q&A session in first half and in second half. Means like for last 20 minutes we can have
okay,
the Q&A session. I will send you the question by shortlisting it.
okay, fine. That would also work. Yeah. Mhm. Okay. So before we dig deeper into the topics, there are four different domains in which you will find your problems to be falling into, namely supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. I will talk in details about these topics in the upcoming slides, but you should note that based on what data you have available with you and the task that you want to execute, you will have to select the algorithm in the domain that is relevant to your problem at hand. While I talk about each of the domain, I will work with the Jupyter notebooks presenting various algorithms and the problem specific data processing and model specific evaluation. Right. Um, so jumping on to the first type, uh, supervised machine learning. As its name suggests, supervised machine learning is based on supervision. It means in the supervised learning techniques, we train the machines using labeled dataset. And based on the training, the machine gives us a trained model, which we use in inference phase to predict the labels for the data which we do not have a label for. So to help you understand on the slides, what happens is the labeled data. So basically the features that we have, the corresponding labels that we have, right? Once we have a data of that type, right, we train a model with that data set, right? Now, once the data model is trained, when we find unlabeled data sets, right, or at the time of inference when we do not have the label for the particular feature list or something, right, column like a list of rows. At that time, we use this trained model to find out the label for the corresponding features, right? So there are two main types. There are majorly two types of the problems that fall in this particular domain. First is the classification, and the other is regression. Let's talk first about classification algorithms. Classification algorithms are used to solve the classification problems in which the output variable is categorical, such as yes or no, male or female, red or blue, etc. The classification algorithms predict the categories present in the dataset. Some real world examples of classification algorithms are spam detection, email filtering. And there are this list goes on. Some of the popular classification algorithms are given below. They would be random forest, decision tree, logistic regression, logistic algorithm, support vector machines, and there are many such type of these algorithms. We will look into the individual examples in the coming slides and the Jupyter notebooks. Now, the second type of algorithm, the second type of classification, second type of supervised machine learning problem is regression. In regression algorithms, they are used to solve the regression problems in which there is a linear or non-linear relationship between the input and the output variables. These algorithms are used to predict the continuous output variable, such as market trend, weather prediction, stock prices, etc. Some of the popular regression algorithms are linear regression, multivariate regression, decision tree, lasso regression. Okay. Yeah. So before we just jump on the notebooks, the advantages for supervised learning would be, since the supervised learning algorithms work with labeled data set, so we have exact idea about the classes of the object, and hence the predictions are better. These algorithms are helpful in predicting the output on the basis of prior experience. Whereas the disadvantages are, these algorithms are not able to solve complex tasks as they are trained on the prior experience. So the classes, the labels on which it is trained on are the only thing that it can execute or give as an output. It can also suffer from overfitting on training data. The model, and in this case, the model may not generalize very well. It requires a lot of computational time to train the algorithm. Now that we have covered basic concepts, let's dive deeper into the Jupyter notebooks. I will just stop screen share and share it again. So for the students who are online or we viewing it and want to replicate this later on, right? They can use Anaconda Navigator, right? They just have to install Anaconda on their systems, get the Jupyter notebook installed, and they just have to click on launch to get into the Jupyter notebooks, right? For now, I will be also using a similar environment, which is basically a Jupyter Lab environment, right? So let me just start that. Okay. So we will start with supervised learning, and first we'll look into classification problems, right? So the very first data set that we'll be looking into is fetal health, right? Just give it a moment to load the notebook. Yeah. Okay. So for the very first thing, what I did is I just upgraded my Matplotlib installation, right? And then the data set that I'm looking into is basically this fetal health data set. So it has basically the outputs which are received from sonography, right? So different. So this data set is there available publicly in a paper published in 2000s, right? So this is the paper is called A Program for Automated Analysis of Cardiotocogram, okay, by J. Matham Pentel. So this data has for each of the different readings which are there, which are coming from a machine, right? So for the fetal body movement, light deceleration, baseline values, severe deceleration, and prolonged mean value for the short-term variability. So there are different. There is a list of features which are given out by that particular machine, and at the end, we also get like we also have a label which classifies whether that particular fetus is normal, suspect for a disorder, or has some pathological condition, right? So they are denoted by 0, 1, 1, 2, 3, basically in the data set. So coming back to it, coming back to the notebook and the installation that we have, right? So I just upgraded my Matplotlib, then imported Pandas, NumPy, Matplotlib, Seaborn, SciPy for the upcoming task that I'm going to be doing, right? So in my current folder, I already have the fetal health.csv, right? So what I will do is at the very first thing, I read the data set, right, using Pandas, then the different columns which are there. So at any time, what you would be wanting to do is first you would wanting to do EDA on top of the data that you have. Any data set that you get, you have to have perform exploratory data analysis to understand what is the data set that you have at hand, right? So very first thing you do is you load a small sample data set in the memory. You check out what are the different columns, uh, what are the different values that it takes, right? So then I basically just do info on the data frame, right? So all the values, so total I have readings like 2126 readings, and all of them are of type float. Okay. Total features that we have are 21, and which correspond to there are 21 features which correspond to the overall health of the fetus, right? Now what we will be doing is we'll be checking out what are the statistics for the data that we have, right? So for each of the column, right, for acceleration, fetal movement, uterine contraction, light decelerations, etc., right? Histograms, the histogram of number of peaks, the number of zeros, the histogram mean, mode, median, variance. So what are the quantiles of it? What is the standard deviation of the values which are provided? What is the min value? What is the max value? That is what we'll be observing, right? So for example, the baseline value the minimum is 106, the maximum is 160, right? And the standard deviation is of 9.8. But then again, like even with that, the mean lies at 133. The first quantile is at 126, and the third quantile is at 140. Right? If you look at Progout decelerations, we can see that the standard deviation is very small, right? The mean value is also very small. It's in the order of 10 raised to minus 3, 159, 1.59, 10 raised to minus 4 into 1.59. Yeah. And till 75th quantile, basically till the third quantile, it's the values are itself are 0. Only the maximum value is of the form 5 into 10 power minus 3. So as you can see, there's not much information which is there in Progout decelerations, right? So that is why you want to do EDA to understand what are the features, what is the distribution which is happening on them, right? So moving ahead, so what I will do is next, like I get some information from the numbers, but it's not like humans are basically visual animals, and it helps the graph when you plot these features on a graph. It would help you understand much more what are the different what is actually happening in the data, basically. So what we do is to verify the distribution, we just plot histograms for all the columns which are there, right? So if we see the baseline value, it's pretty much similar to a normal curve, which is very good for like for any classification problem. It's good to have features which behave in normal distribution, something similar to normal distribution. But if we look at the histogram for acceleration, it's pretty skewed, right? So majority of the values are towards 0, and it has a long tail towards the right side of it. So this graph is pretty skewed. And from the graph we can think of it like to get it into a normal format, we normal distribution, something similar which looks similar to normal distribution. We might want to do a column transformation on top of it. So the different types of column transformation that can be applied to this particular skewed graph is something like log transform, which will transform it into a normal distribution. So that's just an example, but we will continue. Like we'll check out what's happening with the other features as well, right? So fetal movement shows a similar skewed distribution, a lot of zeros, and almost none, like very few values on the for anything except other than 0, right? Now going down, we see a lot of different features which are very skewed, like decelerations. So going down, mean value of short-term variability as well seems like very skewed, and log transformation might help. Okay, histogram. These graphs look fine, like histogram max, histogram number of peaks. These graphs look fine, but anything of that sort of number of zeros, right? Histogram number of zeros. This is a pretty skewed graph, and this variable we won't be able to use it directly. Like the model would not perform better. Like to get the best model, we would have to do some feature transformation on top of it. Okay, going down, we'll just look at all the remaining graph. Okay, now done. Okay, so there were features that are normally distributed, right? Like baseline value, abnormal short-term variability, and some histogram columns. But rest of the features were quite skewed. Is what we have observed. Now, if you look at fetal health as well, we have a lot of we have a very imbalanced data set, right? So for category 2 and 3, we don't have enough samples. Only for category 1, we have a lot of samples, right? So this might pose a problem to get up the best output, the best model, right? So we will do some further analysis to understand, okay, what can be done to remedy this. To understand the variables, like how different variables are interacting with the target variable, right? We will be doing a box plot, right? So basically for each of the feature, like baseline, acceleration, fetal movement, for each of these features, what is the distribution? We'll be checking out the distribution in different target variables, right? In different target classes. So if we look at this graph, right? So in this particular graph, I'll just run this. Yeah. So in this particular graph, as you can see, the first quantile of normal is well below 110, right? But for suspect, the category suspect and pathological, for fetal health, the first quantile is quite high, right? The minimum value is quite high. It's quite high. It's well above 120 for suspect and pathological class. Now we can even see. Okay, before we move ahead on to the other box plot, right? Let me just help you understand. Okay, how to basically read this graph, right? How to read box plot. So the bottom line, this is basically the minimum value which is there in the data, right? So this is the minimum value for baseline value that the normal class takes. Then the point where the box starts is basically the first quantile. Basically all the values which are below this line, right? Corresponding number against this line. So this forms the first 25% of the data that we have. The middle line, which is inside the box, right, is nothing but the median. The central value, and that becomes the second quantile. Like from bottom of the box to the center of the box, that becomes the second quantile. Similarly, the center of the box to the top of the box, this region specifies the third quantile, right? So till this point, you get 75% of the top of the box basically covers the 75%. All the values which are below this top of the box are covering the 75% of the total values which are there in data set, right? And the top line is nothing but the 100th quantile. Basically, this is the maximum value which is there for this normal category. And then the dots which we see above the max and the min line, right, above or below, right? In this, let's say in this particular case, these black dots and these black dots below the lower minimum of the suspect category, right? These are nothing but outliers. So outliers are identified based on the standard deviation, right? So whenever any point is away from more than three deviations, three standard deviations from the median, right? That point is considered to be a outlier in box plot, right? So and that's how it is treated. Now, if we go down, we'll see like for normal, like when we plot box plot for acceleration versus fetal health, we see um, for normal category, it's covering a very good region, but for suspect and pathological, the region covered by the box plot is pretty small, right? And it's very hard to make. It's very hard to understand. Okay, what is going on with the data? The black dots do signify that there are a lot of outliers, but we will see how we can use this information. But then again, like these two features seems like important because for normal category, it's it's very different from suspect and pathological, right? Is what we can see. Now, coming to the other box plot. So in this case, there are a lot of fetal movement versus fetal health. There are a lot of outliers which can be seen here, right? Same goes for suspect and pathological, but it's very hard to make out, okay, what's happening with the data that we have, right? It's very hard to understand the mean, the median value, the first quantile, the second quantile, third quantile, and the fourth quantile of the values which are happening, which the data takes, right? So fetal movement does not seem to be that good of a feature for us to use. Now coming to uterine contractions, right? We can see the median value for uterine contractions for normal category is much higher than suspect and pathological. Similarly, the median value for suspect is the lowest, and for pathological, it's basically in the middle, right? So this seems like a good feature that we can use later on for building the model. Now, if we look at the next feature, which is called light decelerations, and compare it with fetal health, the box plot says the suspect is very different, is behaving very differently as compared to normal and pathological. So this seems like a very good feature to understand. So to basically classify suspect category, and then severe deceleration seems like a very bad feature. So there's not much information which is available in the box plot. So we'll just skip that. Now, box plot for prolonged decelerations versus the fetal health. In this case, normal and suspect don't have much information, but for pathological, there is a wide distribution. So it seems like a very good feature that can be used for building the model, like to identify pathological category. Right. So basically, that's how you interpret box plot, and that's how you use charts to go ahead, like to identify features which should be dropped, which should be kept, what transformation needs to be done, and so on. So I will just slowly scroll down for you to see. Histogram width, histogram min, histogram max. Okay, so all three are very similar, right? The histogram features, the plots are very similar. Number of zeros do not have any information. Histogram mode, mean value, median, medians. Okay, so this histogram tendency, so this seems like a very good feature to identify pathological category. So, so from the box plot that we can see, there are like several features that show variability in suspect and pathological. And so when comparing it against the different classes, like against each other or normal, we are able to make out like with human eye that a particular feature is good at classifying a particular class, right? So, for example, when we talk of normal versus suspect, so we had uterine contraction and light deceleration, which were very different, like which were different to make uterine contractions. So you see, if we look at this uterine contraction, so the normal and suspect, these two categories are very different in this particular chart. Similarly, in this particular chart, suspect is very different from normal and pathological, like for light deceleration. So that is how you identify the features which are important for a particular class and which should not be dropped for anything. So next, what we'll do is we'll check for correlation between the different variables. So what I'm doing is I wrote a function to identify redundant pairs. So basically, what I mean by redundant pairs is like when we calculate a correlation matrix, there would be a same value would be calculated twice in that correlation matrix. So in that case, that is why I wrote this redundant pair function to remove the duplicate values, and then I'm also applying filter on top of it to basically just get me the correlations which are either less than minus 1.5 or more than either less than 0.5 or more than 0.5. Basically 0.5 absolute value as a 0.5. Any value which is greater than any correlation which is greater than this is pretty significant, and hence I'm using 0.5 as a threshold to identify the features which are important, right? The features that we should be looking into, right? So okay. By the way, for correlation, the value goes from -1 to 1, right? -1 would be for any two variables to have a correlation of -1 means if, let's say, variable 1 increases, the other variable would go down in a proportional amount. Similarly, 1 in the correlation would mean if, let's say, variable x increases, then the variable y would also increase in the same proportion, right? So, and usually correlated features are something that we avoid in our training because they would be carrying the same information again and again, like they would have a similar type of information and the variability would not be captured. So yeah, now coming on to the graph, I see histogram width and histogram min have a very deep negative correlation. The value is more than -7.5, -0.75. So both seem to be very inversely proportional, and yeah. So then there is this histogram min and the number of peaks. So this value is also negatively proportional and it's more than 0.5. So it seems like a very significant value. Like significant correlation is there. Similarly, like if we look at the other end of the spectrum, so histogram mean and histogram median, so they have a very positive, like it's nearing to 1, right? So both of them are carrying a very almost same identical information. Then if we look at baseline value and histogram mean, so this is also more than 0.75, the correlation, and hence they are also like very highly correlated, and we would want to avoid having features which are highly correlated. So highly from among the highly correlated features, we might want to delete some of them and test how the model performs, like how the model is trained, right? So with this, we come to the end for the EDA for particularly like first notebook, right? For our first data set, like that is fetal health. So all in all, what we understood here is there were 21 different features and one target variable. The target variable had 3 categories: normal, suspect, and pathological. Several features were not normally distributed, were not similar to normal distribution, and there were a lot of zeros in the values of the features. We also noted that there is a strong correlation between a lot of different features. So we'll have to address that particular concern as well, like before we build the model. We also noted that the data is very unbalanced, and we would have to we will have to balance the data set before we proceed into like creation of the model. Right? So these were the observations that we had from the data that we got, right? So coming to the next notebook, where we actually build classification algorithm, right? Just a second, I will just select the right machine. So the very first thing that I do is I install AutoViz and PyCaret. Right. I'll show you like for this particular demonstration only, like I'm using this to help you understand, okay, how you can at the same time try out different algorithms and then select which algorithm basically fits or solves the challenge that you have better. So let me install it. It's taking some time. Just wait for the installation to go through, and then we'll move. Okay, so the required I will take the questions towards the end.
Yes, sir, no problem.
Yeah. Towards the end of this first half, right? So now that I have the required dependencies installed, so I import some of the dependencies that I have. So basically, I import Seaborn, Matplotlib, SciPy, stat models, basically for classification methods, like data cleaning methods, right? I also import Scikit-learn, and so I will show you how these imported libraries would help us identify, okay, what should be the data processing that needs to be done, right? On the data that we have. So by the way, all the steps, all the EDA that we did, right? So this is the general EDA that you would be doing as a data scientist. Uh, that's part of the data science process. Any data set that you get, right? So EDA is one thing that you would be always be doing on the data that you get, right? Before you do actually build the model, right? Because building the model is very small part of the complete process, right? First, we have to question the data set on, like question thoroughly to understand what is the algorithm that needs to be used, or how better we can improve our performance of the model, right? So just like, for example, a few of the histogram that we saw, right, during our EDA phase were biased, right? They were very skewed. And we know there are the classification algorithms usually, like the classical, like classical classification algorithms uh, do suffer from like perform poorly when the features are skewed, and hence whenever we see something like this, a skewed uh, feature, we want to do some log transformation or something, like some feature transformation on top of it. So that is why EDA is also a very important part of the complete data science process, right? Coming back to the notebook where I would be doing the training. So I import the libraries which are required. I'm using the same fetal health data set, right? I read the data set, starting few values which are there, ending few values. I do again do some normal small EDA to just like we saw histograms and box plot in our first notebook, but there are different EDAs as well, like which can be done, right? So I just do a describe on it, so that shows me, okay, what are the standard deviation, min max values, and so on. So very first I check there are no categorical features, right? So I just leave it like, then I also check whether my data has any null values. So what I do is I just use function is null any. So this returns false, means all the like complete data set is completely populated and I do not have any null values. The D types, all the D types are of float type. Now the correlation matrix that I talked, right? As you can see, like this is a complete data frame that we get, right? But in the form of, just a second. Sure. Yeah. Now you can see there are the correlation matrix is pretty big, right? So all the values which are above this particular diagonal line, right? 1 1 1 1 above this are similar, right? Similar to the corresponding value in the downside. So the range of correlation goes from 1 to -1, right? And we can see this histogram min and histogram width, right? Both of them are -0.9, so they are very highly inversely correlated, right? So you would want to do something about it as well, right? Then if we look at some different value, right? So for example, this 6.2. So histogram min is highly correlated, negatively correlated with mean value of short-term variability, right? So that's how you basically understand, okay, which features need to be dropped or which features need to be like selected. Basically, correlation is one way to understand, okay, to do feature selection, which feature need to be selected for final model training, right? So this is our classic correlation graph. This is basically a heat map. Now coming to the class distribution. So the columns that we have, yeah. So coming to the class distribution. So in the first class, we have 1,655 data points. But for the rest of the two classes, like, right, class number 2, basically suspect and pathological, we hardly have 300 and 200 data points for each of those two classes. And this seems like a very biased data set, right? So we'll see, okay, what's happening with this. We'll check that out, right? How we can resolve it. We will see that in the upcoming slide. So remember, I imported a data cleaning suggestion function, right? So I supplied my data frame to it, and it was successfully, like, for each of the feature which is there, right? It suggests me, okay, what is the improvement that it can be done, right? So it says mean value of log term variability. It's very skewed. The value needs to be capped, or or we need to drop the outliners, right? And then fetal movement. This is a very highly skewed data set, like feature. So we need to drop the outliers or do some Box-Cox transformation to get to a distribution which is very much similar to normal, right? Similarly, it gives us a lot of different suggestion on the features that we can do, like the feature engineering or any kind of engineering that we can do for data cleaning, right? So it gives us that. So what I do is, now that I know what's happening, for the sake of simplicity, I won't do any feature engineering right now. But what I will do is, because there is a highly imbalanced data set, what I will do is I will basically oversample it, right? So that's what. So I will apply SMOTE algorithm to oversample. Okay. So before I move ahead, what I would want to do is, I will share with you, okay, what SMOTE, what actually that means, right? So just give me a moment. I will share my slides again. Okay. So it's like, to overcoming class imbalance, like we saw over the data set that we have, is highly imbalanced. And so why imbalance in the data set is even an issue? Let's start with that, right? So let me give you an example to help you understand this particular accuracy paradox that will happen, right? So suppose you are working on a health insurance based fraud detection problem. So in such problem, what will happen is, you will observe that for every 100 insurance claims, 99 of them are non-fraudulent, right? 99 of them are genuine claims that are made, but there would be one claim which would be fraudulent. Now, let's say if you build a normal binary classification model, and which won't be any complex, right? It can just classify everything as non-fraudulent. even at that point, you would just get 99% accuracy, which is quite good. But if you think about it like that, we are still allowing fraudulent transaction, which is this clearly is a case where data distribution is very skewed and accuracy matrix is not the right matrix which can be used to measure this measure the performance of the model. And in the industry, it is not generally preferred to use accuracy when the data is skewed. So to deal with this, resampling is one of the method which is most commonly preferred. Preferred. And basically, resampling is the approach which is most commonly preferred to deal with the imbalanced data set. So there are broadly two types of resampling that can happen. So first is basically undersampling, and the other is oversampling. Now, in most of the cases, oversampling is preferred over undersampling techniques. The reason being, in undersampling, we tend to remove instances from the data, and this and like when we remove the data set or when we shorten the data set, we would be removing some important data points which might carry some important information for the final classification as well. Hence, usually oversampling is the go-to method. That is like oversampling is the method that is preferred. Now, there are many methods for resampling, right? But the two most popular methods are synthetic minority oversampling technique, right? Which is short form is SMOTE, right? SMOTE is an oversampling technique where synthetic samples are generated for the minority class. In our case, the class 2 and class 3, basically suspect and pathological. These classes are the minority classes. They are very less in number, and hence they are minority class. So what SMOTE would do is SMOTE would generate synthetic samples for this minority class. This algorithm helps to overcome the overfitting problem posed by randomly oversampling on the data set that we already have. SMOTE focuses on the feature space to generate new instances with the help of interpolation between the positive instances that lie together. So what I mean by that is, let's say SMOTE is oversampling, right? And for a particular feature, it wants to generate a synthetic value. So what it will do is, for the same class, it would look for examples which are closer, right? So it would look for two examples which are closer to each other. And what it would do is it would do something similar to calculating the mean between these two values and assigning it as a synthetic value for the new synthetic sample, right? So it's not this which is happening, but this is the to understand it in simple terms, that's what it is being doing underlying under the hood, right? So I won't go deeper into the theory part of it, but SMOTE as an algorithm is available for you to use, right? So just remember, SMOTE generates synthetic example by interpolation between the positive instances that are together, that are closer, right? And then the second type is adaptive synthetic sampling approach, right? ADASN. So this ADASN is a generalization of SMOTE algorithm. So this algorithm also aims to oversample the minority class by generating the synthetic instances for it. But the difference here is it considers the density distribution when generating the new sample. Due to its consideration of the density distribution, it helps in adaptively changing the decision boundary based on the samples which are difficult to learn, right? So this like learning, like selecting the synthetic example totally based on the distribution, right? So this is particularly the major difference between Audacian and SMOTE, right? I understand that there would be questions about this, but let's take questions later on, right? So I will quickly jump to what is next. Okay, so both of them, SMOTE and Audacian, are quite heavily used in the industry for generating synthetic example to get model perform better on the generalized, on the unseen data set, right? So it's being used widely in the industry. So let me just quickly jump back to my notebook. Yeah. So remember, like we had our distribution was quite skewed, right? For the two features, basically. Just a moment. Okay, so the two features for which our distribution was skewed was, yeah, suspect and pathological. Right. Sorry. So what I do is to use SMOTE, you just import it from I'm imbalance learn, and from oversampling class, SMOTE is the algorithm that is available, right? So I fix a random state and just do a pre-train sample. So I supply the original train and original training data, right? X and Y column both, and get the oversampled the new data set that we have. Let's say if I run this, so as you can see, previously the class distribution were like 1 1 3 2 2 2 3 1 1 4 7. This was the previous, like the original training data set. But once the over resampling happens, all the classes have 1322 rows, right? So that is how I got the, like now the data set is quite balanced. So with this, we can move to the modeling, like how to basically to build the models. So what I would do is I will just prepare my data for the training from PyCaret library. I will use from classification. I will use some of the functions which are there available for us to use, right? So yeah, so here I just did a setup. I provided a train data. I provided what is the fetal health. I provided a session ID, and I also did basically I allowed the algorithm to normalize before it created the training, right? So what it did is, okay. So what it did is like it gave me a bunch of information for this, right? So this is a CPU job, the number of folds. So what's happening internally is like it's doing a stratified k-fold evaluation, right? So number of folds are 10, right? The normalization which was used is z-score, right? The imputation, the numeric imputation, the categorical imputation, what will be done are given, right? Simple mean mode and so on, right? Now once that my models, like the models which are available from PyCaret are ready, right? What I just do is I basically just run compare the models. So internally it would run a lot of different algorithms on top of the data that I have already provided. So as you can see, it's running random forest, decision tree, k-mean algorithm, like KNN classifier, Adavos, logistic regression, and so on, naive-based, SVM, linear with linear kernels. So it's running in the background like different algorithms, and it's basically giving me the list of what are the matrices on which I can measure it, right? So in this particular case, light GBM, basically light gradient boost machine learning algorithm, is performing the best, right? It is basically giving us the best output. So I think this is hard to read, but as you can see, the extra tree classifier, right? So the accuracy is 97.62. The AUC is basically 99.87. The recall for this is 97.62. So it's pretty high. So I will get to what recall precision and F1 score means, but for now, and think of it like whenever there is imbalance in the data set, F1 recall precision are the values, AUC are the values which are basically, AUC is nothing but area under the curve. So these are the matrices which are used to compare different models. So right, what I will do is I will just fetch light GBM model independently, right? So I just run the light GBM model independently, and so it gave me a lot of different accuracies in the different folds, right? So we are doing a stratified k-fold evaluation, right? So in first evaluation, the F1 score was 99.28. The second fold was 97.14, 98, 97. So all the values are very high, top class. Like this model has been put best with light GBM, right? So finally, like we can see on the training data set, the F1 score that we are getting is basically 98.63. So we'll plot just a second. So we plot light GBM. Yeah, so this is particularly the ROC curve for light GBM. So ROC curve is nothing but basically true positive rate versus false positive rate. I will come back to what true positive rate and false positive rate is. But let's say any classifier, right? Whenever you plot ROC curve for it, the plot should be towards 1, right? The area under the curve should be 1. So this red line that we see, right, on this top, it should be as close as possible to the value 1. It would be first, the plot would be like straight to 1 and then straight line. So basically ROC for the class 0, in this case the AUC is 1, the ROC curve for class 1 is basically this green, light green line, which is not visible to us, but the area under the curve is approximately 1. Same goes for the class number 2, right? The AUC is 1. Area under the curve is 1. So the model that we have obtained is very good model. Then we plot for errors, like what the mistakes are being done by the model, right? So where the places where the model is basically making the wrong predictions. So as we can see from the total test predictions that is made, right? There is a, like in class, in basically the second class, in the basically the pathological class, there are no misclassification. But for suspect class, there are some which belongs to the normal class, right? And there is at least one example which is from pathological, which is classified as suspect, right? So these are wrong predictions that are made by the model for on test data set. Right. Similarly, for normal, there is at least one bad classification that has been made, right, which actually belongs to suspect class. Now, if we look at the learning, right, how when the model was training, how the cross validation score was, what was the plot for it? So as you can see, the training during the training, the model was like AUC was top, right? It was just one throughout. But as the model trained, right, on the cross validation score, the AUC kept increasing, right? So the value of AUC kept increasing, and it basically improved over the time. As the training went by, it improved. Now validation curve, right? Similar to what we saw during the learning curve, we can see as the training went by and as the depth increased for the light GBM classifier, the AUC score increased slowly. Like for training, it went by quickly. Like by the fourth, when the max depth value is 4, the like AUC for the training was already on the training data set, it was already 1. But as the max depth increased, the AUC for the cross validation also increased. So these are the plots for, like, this is how basically you understand the plots for the model which are trained by PyCaret package, right? So I know this was a lot, like there was a lot of things that we discussed, and I left few things, right? So for a particular example, like what is F1, precision recall, like why they are important, right? And so on, like few other things as well, right? Plots and everything. So let me switch back to the slides. Okay, so precision recall and F1 scores. What does that mean? How are they calculated and so on, right? So let's say when the actual value, I will just create a pointer, yeah. When the actual value is 1 and the model also predicts 1, then that is basically a true positive type, right? When the prediction is 0 and the actual value is also 0, then it is basically a true negative, right? Now here further it gets complicated, right? When the prediction is 1 but the actual value is 0, this is when this type is called false positive, right? And similarly, when the prediction is 0 but the actual value is 1, we call it false negative, right? So explanation would be like, let's say whenever there is a false negative, case of false negative, it basically means the prediction was negative, but the actual value was positive. Similarly, false positive is the prediction was positive, but it was actually negative, right? So just keep this in mind when we go to the next slide, right? So if you can see, the precision recall, we use false positive, true positives, false negatives to calculate the precision recall and then F1 score, right? So from this chart you can see, okay, this true positive, false negative, true negative, these values have some link to precision recall and F1, right? So we'll just see that what that is in this slide. So precision is nothing but true positives, total true positives which are there, divided by true positives plus false positives, right? So this can be interpreted as number of correctly predicted positive instances, right, divided by number of total positive predictions that were made by the model, right? So to put it simply in words, precision is the measure of how many positive predictions that are correct, right? So let me reiterate. Precision is the measure of how many positive predictions that are correct, right? So that's the ratio. So this ratio signifies nothing but how many of the positive predictions are correct, right? Now coming to recall. So by definition, recall is the measure of how many positive cases that the classifier correctly predicted over all the positive cases in the data, right? So do note there is a subtle difference between the definition of recall and the precision, right? But this is a very important metric. Both precision and recall are a very important metric which are to be used. Like you'll see face them often in the industry, right? You'd have to use them often. So let me reiterate. Recall is the measure of how many positive cases that were classified correctly over all the positive cases in the data, right? So that's nothing but true positives by true positives plus false negative, right? So basically that is nothing but number of correctly predicted positive instances, right? So this is correctly predicted and divided by total number of positive instances in the data set, in the ground truth, right? So in this case, the difference is the denominator. So in precision, the total positive case predictions are made by the model, and in recall, the total positive instances that are there in the data set. So this is the major difference here, right? So then comes F1 score. So now, as you can see, like as you can feel, like precision recall seems like both of them seems to be inversely related to each other, right? So let's say what usually happens is when precision gets high, the recalls falls down, and when recalls falls down, sorry, gets high, the precision falls down, right? So this is a problem that often that takes place often. So F1 score was a measure created to combine both precision and recall. It is nothing but the harmonic mean of these two. Harmonic mean is just another way to calculate an average of values. So, so it is generally described much harmonic mean is described whenever the ratios are involved, right? So than as compared to traditional arithmetic mean. So the idea behind F1 score is to provide a single metric that the weights of the two ratio that basically weighs in the two ratios in a balanced format, requiring both of them to be high when the for F1 score to be high, right? So this is very important. So like I would want you to like take a moment and understand it. Let me just reiterate what precision is. Precision is the measure of how many positive predictions that are correctly made by the model. Okay. And then recall is the measure of how many positive cases that the model identified correctly over all the positive instances that are there in the data set. Right. So one precision talks about the ratio of correct predictions done by the model, but recall talks about the correct predictions when compared with the total positive cases that are there in the data set, complete data set. Okay. I will switch back to my notebook. So that was all for classification. So I believe there would be a lot of different questions, but let's take them at the end. Okay. Just a second. I will open my notebook for regression. Just while my notebook loads. Just a second. Okay. So now, yeah, screen is visible. That's nice. Okay. Yeah. So the second type of supervised algorithm is regression, right? So there are multiple different regression algorithms which are there, right? Depending, just like how we saw in our classification problem. But now, as you can imagine, right? Previously for classification, there were discrete classes. The classes that we're predicting were categorical in nature. But in case of regression, the classes that we are going to be predicting are continuous. Sorry, the target volume column that we are going to be predicting is continuous in nature, right? So as you can imagine, the evaluation matrices associated would be different as well, right? So we will check for the associated evaluation matrices later. But for now, let's continue with the data that we have, right? So correspondingly, like because the target variable is continuous in nature, the EDA would also slightly change. So we'll just get started first with the EDA. So the data set that we are going to be using for this is HR data set, right? So human resource data set on from a particular company, which is right. Where in this case, the data has for each of the employee ID, whether they are married, gender, employee status, department, what the salary is, the position, what is the state, zip code, date of birth, then so on. So it has a lot of different information, right? Date of hire, date of termination, what was the reason for termination, the employee status, like the employment status, and so on, right? So the total leaves that they have taken, the recruitment shows the performance, how they are doing, right? So this data set has all of this. So this data set is open available, like open source and available for you to use. But I will try to give you a flavor on how to do the EDA with this type of data, or like for a regression challenge. So for the very first thing, what I do is I basically install the required libraries. So in this case, I'm using pure waffle and Squarify. Then I import Matplotlib, warnings, Plotly, and so on, right? Then I just read the data set with Pandas, right? So this is something that I just discussed, right? So we have the, like, for each of the employee, like what would be the necessary details that are to be stored, right, for any HR. So this particular term. So the basic EDA that I will be doing. So the shape of the data set is just 311, and there are 36 different columns, right? So you can, as you can see, so some of the columns are object, right? So basically they are string. Remaining of the columns are either, so remaining of the columns are integer or float, basically numbers, right? So none of them, only manager ID, some of them have non-null count, right? So for rest of the features that I can see, all of them are full, like only like date of termination, maybe only 104 employees left the company, but rest of them did not. Hence, I concur that, like, I have a feeling that date of termination value is null for them, the employees which are currently still in the organization, right? Manager ID, maybe some employees are high enough that they don't even have the manager, right, high up the in the chain. So maybe that is the reason why the manager ID for a few of the employees is null, right? So then once that is done, like from this preliminary understanding of the data that we have, right, we'll just see, okay, what is the, for the numerical features, what is the mean, median, mode, like the 25, the different quantile which are there, right? So for zip, it doesn't make sense, right? So we can just ignore zip. We can even ignore manager ID or employee ID, married ID, because they don't make sense, right? Even gender status doesn't make sense. So we'll just ignore that. Absence is something that should be noted, right? Then days left, late last in the 30 days. So it's mostly zero only. This is a very skewed column. Okay, like numbers are fine. Let's look at the graphs, right? So we'll just move. Okay, so what I'm doing with this column, cell number 10, is I'm selecting all the columns which are of the type object, and then basically strings, right? And then I'm selecting all the columns which are of the type numbers, basically either integers or floats. So I can see that there are total 18 columns which are categorical, basically string, and there are 18 columns which are numerical, right? So listing out all the numerical values. So checking for the unique values which are there in numerical columns. So employee ID, yes, each employee will have a unique employee ID. So 311. Married status, yes, a person can be either be married or not married in this particular data set. So just two values, right? Gender has two values. Okay, that's fine. Department ID, okay, that's fine as well. So there are 6 different departments. So zip codes are a lot of them. Manager ID is, so okay, there are 23 different managers which are there in the organization. And then we look at the categorical columns, right? We'll just see, okay, what are the different categorical features and what is the unique count in them. So I see, like, employee name would be unique. Okay, that's fine. Position, there are 32 different positions. Sex, that's fine. Gender, department, 6 different departments. Manager name, okay, 21. Okay, so this is fine. Like, I guess I think, like, the employee name and employee ID are something that we can just directly ignore, right? Because they are not of any use as such for us, but basically they are of use to uniquely identify a row, right? So they are primary keys for our data set. So some of the hypotheses that can be made on top of this data is, how are different people, like different employee, like what is the count of different employees in each position, what is the count of employees in each state, right? Female to male gender ratio within the company, female to male gender ratio for the pay gap which is there, the age distribution, the department wise count of the employees, like, right? The pay rate with, like, how does the uh, pay differ depending on the manager which is there, right? Also depending on the manager, how is the different score for the employees, right? The basically the performance metric for the employee. And then we'll also see, okay, how many terminations that are, like, termination for for a particular manager, right? So these are some hypotheses that we feel, okay, that might be important. So these are the charts that will basically plot. So the very first thing will count the different employees in each of the position. Okay, so okay, we'll just run this cell again. So this is the chart which is there. If we see, look at it, production technician 1 is the highest number of employee, like it has the highest number of employees. So it has 137 employees, followed by production technician 2, which has just 57. And if we go towards the right, uh, IT manager infra to data analyst, right? All of them have just one employee. The rest of them has like 2, 3, 2, 3, 4, 5, something like that, right? So IT manager, database, senior database administrator, sales manager, like there are just 3 sales manager. So we can see, okay, depending on position, like most of the employees are production technician 1, right? So okay, so this tells us something. Let's look at the other charts as well. So we'll just see, okay, what are the employees in different states. Okay, so from what we can see, like from around 311 employees to 76 employees are just from one state, I mean Massachusetts state. So feels like the company is based out of Massachusetts itself, like has heavy operations within Massachusetts, and rest of the state is like very minimal. So must be like salespersons or something. So we'll come to that, right? We will see, okay, what is the, will, like, we know, okay, Massachusetts has the highest number of working employees. So we'll just see, okay, what are the different departments across different states, right? So depending on that, that would help us to understand, okay, how this is functioning, the company is functioning. So I'll just plot. So this particular data frame is nothing but it tells us, okay, for each state, what are the different departments which are there and the total count of employees which are there. So for example, Connecticut, like CT, has IT sales. So there are, for IT, there are 5 people, and for sales, there is just 1 person. But for majority of them, only salesperson is there in the complete state, right? For Massachusetts, there is admin office, executive office, IT, IS, and yes, production. So there are 209 employees which are there in production and 11 in software engineering. So for rest of the states, mostly it's to deal with IT services only. So yeah, okay. So we can concur, like we can safely concur that this particular company is Massachusetts based, and it has all its operation in Massachusetts, and all for the remaining state it's just sales. The sales executives are there, and even within the all the different department, production is the only department which is like this particular company hires a lot for production profile. So we'll see, okay, the distribution of within the Massachusetts department. So production has 209, 44, 11, 9, 2, 1. Okay, that's fine. That's good. So we understand Massachusetts. Now let's move on to another variable. So let's check out the gender ratio. So we can see 56.59% of the employees are female, okay, and 43.34% of the employees are male. So now this particular numbers in this graph would look like something like this. Okay. So this organization has more females than males. That can be safely concurred. So now let's just look into the count of employees under different managers. So the count of employees under different managers, so we can see like manager number with ID 30 and 3, right? They're not doing much, so they just have one employee under them. But for rest of them, that's more than, like, on average, it's more than 10 employees they're managing, like at least more than 5 employees they're managing, right? 6, 19, 17, 14. So for almost all of them are greater than 4 or 3. That's fine. 5. Okay. Now coming to department-wise count of the employees, right? So what we'll do is just run this. So what we can see is department-wise production takes up the maximum amount of employees which are there, right? Followed by IT, then sales, and then so on, right? Now we know now that production wing of the company is like quite big. Now let's check out the date of birth of the employee. So we'll just take the DOB date of birth column. We'll convert it correctly. Now we calculated the age using today's date and the date of birth that was there. Once we get the ages, what we do is we plot the ages. So what we can see is we see something, a graph like this. So what we can concur is a lot of employees, like the good chunk, like at least 50% of the employees are between 35 to 45. So this is basically a density plot. Okay, now let's just check, okay, what is the distribution of pay scale of various employees? So let's say depending on the gender. So what we can see is there is this red line, which is for female plots with this density. We can see like females are earning more than male because this yellow line, the graph is quite low and has a long tail, or red line as well. So yeah, so the red line extends quite a bit outside, right? Out of in the higher bracket. So females are earning the highest salary, and the number of females are also high, right, in general. though the mean seems to be nearer, like the mean salary, but the highest earning employee is a female, is what something that we can concur. So let's check that. So what we can do is we will plot a Boolean plot next to understand that, right? So we see the mean of both male and female are closer, right? Closer, like in the same range. It's not far, like it's not up and down, like there is not much difference. So the on an average they are earning similar, but as we can see, like for female there is a long tail, right, which goes above $2,500,000. Whereas for male, the tail ends just short of $200,000. So we can concur that male are earning less than female. So we'll just check who is the highest earning person. So we have this name, Janet King, with certain employee ID. They are earning the highest, right, in the company. Now, let us check the pay scale with respect to the manager that they are working with, right? The average pay employee is getting under a same manager, right? We'll just check that. So that is what, so the average salary, like for each of the manager, what is the average salary? We calculate that. So for each manager, the total employees that they have and the average salary that they have, that the employees under that manager get, right? We just calculated that, and now we just plot it in the graph. So as we can see, the highest mean salary is corresponding to the manager with ID. It is between 5 and 10. I guess it's most probably 9. So manager with ID 9 has the employee which earns the highest. Basically Janet. Okay. Now, so let's now check out the performance score of the employee depending on the manager, right? So like how the employees, how different teams are performing with respect to the manager. So we'll just take the performance score, run this. We'll see, okay, what are the unique values which are there. So exceeds, fully meets the expectation, needs improvement, PIP. Okay, PIP is nothing but a performance performance action plan. Okay, so what we'll do is we'll just map these values to a number. Exceed is mapped to 4, fully meets mapped to 3, needs improvement to 2, and PIP to 1. Okay, so the PIP is the poorest and exceeds is the highest, right? So once I do that, I run this cell, then I just get the head, like I get the data, and now basically for each of the manager, the performance score depending on the employee count, right? So, right, what are the, for each manager, for each performance score, total employees which are getting that particular that score, right? So in this case, manager ID 1, the third is nothing but fully meets, yes. So for manager ID 1, there are total 6 employees which are meeting fully meets performance score, right? Similarly, for manager 2, there are 2 employees which have needs improvement. There are 13 employees which meet the expectation, and there are 4 employees which are basically exceeding the expectation. Similarly, rest of them. So numbers are fine. What we'll do is we'll have them plotted. So plots are much more attractive, right, from the numbers. So I basically, in this particular data set, I basically just remove, like, I split it into 2 parts. People who are rated 3 and above, basically fully meets and exceed, are good, like they are pretty safe. But which are below 3, basically need improvement, or they have a rating of PIP. So I segregate the list into 2 parts, and then I do count of the employees for good and bad, right? For good, total, like for each manager, like what is the count of employee in that particular good or safe zone. Now what I do is I plot them. I plot those 2 graph. So for the very first thing, the count of underperforming employee manager, depending on the manager. So 5 is the manager ID, and this, however large this particular width is, it tells us about the total number of employees that are underperforming under that particular manager. So 12 has the least number of employees which are underperforming. 5 has the highest. 5 to 19 has the highest, right? Similarly, for good employees, you can see 3, 18, 20, and so on, right? If we look at the numbers, so 3 has 1 employee which is performing bad, but then he also have 70 employees which are performing good. But then 18 has 20 employees which are performing good, and none of the bad employees, none of the employees with poor performance. Okay. So with that, like, we plotted it. So finally, we just check out, okay, we are towards the end of the EDA. So we just check, okay, how is the performance gender-wise, like how the split is, how is the performance gender-wise split looking like. So we just plot this particular data frame. We'll just wait for it to, yeah. So as we can see, generally, like, females are higher in number for, like, we can see, like, poor performance is given by men, like the which are falling in the fifth category, there are a higher number of men. But as we move to the right, needs improvement are same, but then meets expectation, exceed expectation. For both of them, women are doing better, right? So this is some plot that we have. So with this plot, we can firmly say that women are more efficient as compared to men, right? Then let's just check whether the date of termination has any connection with the manager, right? So we just check that how long the date of hire and date of termination, then the termination reason. We just pick that as a data frame, right? So if we group the employee IDs, basically if we group the count of employees for different terminations, So 20 employees moved to another position. Return to school, there are 5. Then there are 14 employees which were unhappy and hence left. And there were 11 people who were pushed by the competitor with more money, right? Now, basically plotting this, so you can see there were like nearly 5 employees which were retiring due to performance. There were nearly 5 employees which left. Highest, like the 20 plus people moved to another position, right? Then comes the 14, the people who were unhappy, right? 14, yeah, this one, right? So this is the chart. So funny thing is there is an employee that learned that he is a gangster and hence left. So there is one employee which were terminated because he was a gangster, like some crime member must have a police history. Okay, so next we'll check. Okay, where were the people, like most of the people leaving from, like which particular department? So department wise, what is the count? And we'll just plot that. So so this does not seem to be a major change from what we expect, right? Production, the majority of the company consisted of employees from production department. So highest number of people are leaving from production department itself, followed by IT, sales, software engineer, and then finally admin officers. Okay. So we will next see, okay, when were the employee joining? Like what is the distribution according to the year of when they joined? So we extracted that particular information, right? We grouped them by year, like date of hire, and then count the employees which are there. So what we can see is, yeah, in 2011, the company hired the most, right? So it hired nearly 80 plus people, followed by 2014, where the hiring was total 60, and then 12 and 13, which had 45 and 44 respectively, right? So 2011 seems to be the golden year where the company grew a lot, right? Nearly 50% company grew. Okay. Then what we do is, uh, okay, like depending on the year, like what is the distribution, like when was a particular percentage of the company was hired, right? So just another plot which gives us the same information as the previous plot. So this particular visualization is called baffle visualization. Baffle plot. So what we next do is we just create a heat map of the correlation, right? Which of the numerical features which are there. So we will just check out, okay, what are the highly correlated features which are there. So performance score seems like to be highly correlated to days late, right? In negative value. So negative 75. So let's say if the person is the number of, let's say if the value of the person, this day late in the last 30 days is high, then his performance score is bad, right? Is what something that we can concur. And then there is this engagement survey with days late last 30, which is still minus 0.59, which is high, right? And then we have this thing, special project count. So let's say that's very much correlated to salary, right? So let's say if a person is having employees having doing some special projects, the more special project they do, the more salary that they would be getting, right? So that is how this particular value means, correlation means, right? So these were some of the important observations from the data set. Okay, so then we plot the special project count with salary and how it differs over sex, like different sex, whether male or female. So what we can see is there's not much differentiation between the gender, right? So it's like more special count. Okay, so the more the graph is trending upwards actually. If you look at it, the graph is trending upwards. So the more special project they do, the higher the average salary it is for that particular period, right? Okay. Okay, so that was all for the EDA for this particular human resource data set. So let's check out the how to basically build the model with the data set, right? I'll just a second, I will open that notebook. Yeah, now that the notebook is loaded, yeah, I will run these cells one by one. So initially, I'm just loading NumPy and Pandas, right? To load the data, like seeing the files which are there. I then load Matplotlibs, the train test split from Scikit-learn, Seaborn. I read the same data, HR data set that we just saw. We just did the EDA on. Same data set. I list the columns which are there. So in this particular regression challenge, we'll be basically predicting salary, right? So how different, like how, depending on the different values which are there, how the salary would be affected, right? We will just regress on that salary. So from the features which were there, employee name, employee satisfaction, emergency survey, and so on, date of termination, employment status. So we just ignore these particular columns for now, like to we ignore these columns and we don't build model using those. For now, we will just use marital status, gender, whether that person has been terminated, what is the position, the department that they are working on, what is the performance, right? The absences that they have taken, and the special project they are doing, right? So we'll just use these columns to create the model, right? And then basically I'm just extracting the target feature into X and Y, right? And then like, so I have some categorical features which need to be encoded, right? So column transformation needs to be done for sex, department, performance score, right? Column transformation needs to be done. So what I do is I just import the column transformer and one-hot encoder and give the list of columns that I want to apply this on, and then create the train test split, right? So once this train test split is created, what I do is I import some bunch of different regression algorithms which are there available in Scikit-learn, right? So I start from random forest regression, k-near regression, linear regression, I also import SVR, linear SVR, lasso regression, res regression, right? So these models with there. Then decision tree regression, random forest regression, right? So I import all of them. What I do is I set up them as a list, right? So I set most of them with default parameters which are there, right? So this can be changed. So this is for a demonstration perspective to with different algorithms how simple that training can be, right? So I just do this, yeah, and then one by one I do a training, right, and then do a prediction. And once the prediction is done, to evaluate, right, I'm calculating, explain the basically the how much of the variance the particular regression, like the prediction is capturing, right? I'm also using mean absolute error, which is another evaluation metric, and then I'm also doing I'm also calculating R2 score, right, for calculating the performance of different models, right, to compare. So I just ran that. I will get to each of these, right? What these value mean, right? What these are one by one. So what we'll see is very first linear regression was running, right? It trained in like very small time, like it's like 0.016 seconds. The prediction was almost in 0 seconds. So the variance that it explained is 0.14, 41% basically, right? Mean absolute square, right? So this is like uh, 12,169. The residual sum of square is a pretty big number, so I will just skip that. But the R2 value is 41, like 0.41. So okay, before I go over okay what model is like which model is better and so on, I will just brief you on what each of these evaluation metric mean, right? Okay, coming to this. So variance is basically a measure of, so you need to understand like these matrices in order to determine whether a regression, whether the regression model that we just built are accurate or misleading, right? So very first thing is variance. In terms of linear regression, variance is a measure of how far observed values differ from the average of the predicted values, right? So this means their difference from the predicted value mean. So the goal is to have the value that is lower. So lower the variance, the better, right? So this how low this value of variance should be. So that is particularly quantified by R2 that we will see. So that we will see next, right? So R2 is nothing but, so what is R2? So R2 is a value which varies between 0 and 100. It is closely related to mean square error, but it is not the exact same value, right? So another definition for R2 would be total variance explained by the model, right? And the total variance of the data that we have, right? So if we say the R2 score is 100%, then the two variables are perfectly correlated. That is, there is no variance at all. By that it means the predicted and the ground truth are same, right? Like they are having the same variation, and hence the variance would also be low, and hence the R2 score would be 100%, right? a low value of R2 shows a low value of correlation, means that the regression model is not valid. Basically, it's not good. The low value of R2 signifies the model is not performing good. Right. So in terms of mathematical example, okay, on the notebook I will show you the mathematical equation for this. But okay, let me just cover up what is mean square error. So mean square error is nothing but basically the average of the square of the errors, right? So the larger the number, so larger this MSE value, the larger the error is. So error in this case means the difference between the observed value, like basically the ground truth, minus what the predicted value is, right? And squaring of it. The squaring is done only to the difference, like the difference between the predicted and the ground truth can be negative or positive, right? So to use the absolute value as well, like so mean square error is just absolute sum is also a metric, but mean square error functions better as compared to mean absolute error. Hence, we just use the difference and square it, like predicted value minus the ground truth and square it, and the sum of all such errors. Right? So that is basically the mean square error. Okay. So what we'll do is, I'll go back to the slide. Sorry, go back to my notebook. So now with the information that we have, right, we will see this linear regression. We'll just right now use R2 to compare different models which are there, right? So R2 for linear regression is 0.41. It's not bad, but not that good as well. Ransack regression is in negative, so that's pretty bad. That's very bad. And then if we scroll down, SVR is bad. That's a negative. Gaussian is negative. So for decision tree regression, there is this 0.57. So this seems to be a very good model. And then random forest regressor is like at 67%, right? That feels like a very so random forest regressor is the best performing model for our use case, right? So the variance is also explained, which is high. The mean absolute error is also low as compared to different models which are there, and same goes for the residual error sum as well, right? So random forest regressor in this particular example is working best, right? Yeah. So as we know, like I just talked about mean square error, right? The formula. So what we're doing is mean over all the examples, right? So for example, to write mean square error as summation I goes from 0 to n. Okay, so we are basically summing up all the values multiplying it by 1 by n. So basically we are calculating an average, right? So that's what 1 by n into what we do is prediction for ith example minus ground truth for the ith example, test example, right? And that is basically squared, right? So MSE is basically following this particular example, right? So this is the MSE part. Now, see, what we do is we use MSE to calculate the R2. So we'll just we just use this R2 equals to Same thing, like, okay, we will use, I will just create a variable v, which says how is the mean of the predictions performing, right? So like, as in our ground truth data set, how are different, like what is the variation which is there, right? So what I do is summing up all the values, summation I equals to 1 to n, right, multiplied by 1 by n multiplied by the mean, np dot mean of the ground truth. The mean of ground truth. So all in the ground truth values, what is the complete mean minus the predictions for I. So this is my variable v, right? So what I do is I use v and MSE to calculate R2. So R2 is nothing but 1 minus MSE by v. Okay. So that is the mathematical form of how R2 is calculated and why it is basically using to capture the model performance. But then again, it should be noted, there is no physical relationship that having high R2 would be the best model, right? So usually having zoom screen. Okay, I got a message that zoom screen is not visible. Let me reshare my screen again. I have reshared it. Okay, so yeah, so this is the particular. Is my screen visible now from the host end?
Yes, sir.
Okay. Yeah, great. So this is a particular formula for calculating the R2. Okay. So okay, we digressed a bit, but okay, let that be. So till now, what we saw what comes under supervised algorithms, the different classification methods, the evaluation method for classification. We also saw like what are the matrices which are to be used when we are facing a classification challenge, right? What the classification algorithms are, right? What all it entails and everything, right? Then in regression, we saw like what are the different EDAs that needs to be done, right? Same goes for classification as well, classification challenges.
Excuse me, sir. Sorry
Yeah.
to interrupt. Actually, students are saying that the screen is not visible. Means, the visibility would be much better, they are saying, and means they are asking you to zoom the screen.
Oh, okay.
Yes.
Okay, hope that's better now.
Okay. Please put in chat box if the screen is visible to you all.
Okay, I will check that next. But okay, to summarize, till now, under supervised machine learning, we saw classification challenges and we saw regression challenges. First of all, we saw what should be the EDA. Like I would put heavy emphasis on EDA, like exploratory data analysis. So that skill is not something you would learn from the book. It totally comes from us ourselves asking question to the data set, right? So we challenge, poke the data to give us the answers on the behavior. So once we get that, we know, okay, what are the transformation that can be done, right? So then post EDA, we saw what are the different algorithms that are there in classification. We didn't go much into the theory for the algorithms, but we saw, okay, how we can apply those algorithms and just basically select the best working algorithm for our use case, right? Similarly, we saw same thing for regression as well. We saw different EDA methods which are to be done for regression challenges. We compared different regression algorithms against each other with evaluation matrices like R2, variance, MSE, right? So with that, like, let me just take on questions which are printed. Okay, just a second. I will go to the YouTube. Hmm. So what I will do is I will take the questions that were given there. I think. Okay, so I'll just take the questions which have passed on to me. Okay, so is ML dependent on each other? So as I said before, there are different classes like. So there are for any machine learning challenge, a problem that you would be facing would be mostly falling into either of these four buckets, right? It would either be supervised, unsupervised, semi-supervised, or a reinforcement-based learning example, right? So it totally depends on the problem that you'd be getting. So depending on that, like, let's say if a continuous, let's say you have the labeled data set, right? So then supervised is the method that you would be going into. But let's say if you didn't have a labeled data set, then unsupervised learning is the way to go. But yeah, all of them are independent. I will dig deeper into unsupervised, semi-supervised, and reinforcement in the next part. But each of the stream is independent, and each of them addressed a different kind of challenge which is there. Each of them have a different advantage and a different disadvantage as well. So how we know when will the session for data scientists? So how this session helps for data scientists is, see, as we are going through the notebooks, I'm walking you through the steps as a data scientist that you'd want to take in the job, right? In the industry that you'll have to take. Like once the data, like nobody would tell you, okay, these are the steps that you should be following on the job. It's something that you'd have to start asking questions yourself, right? So let's say in Mintra, the fraud needs to be detected. So Mintra just know, okay, their database got leaked, and they just need to identify, okay, what type of fraud has happened. So nobody would tell any data scientist, okay, this is the type of fraud which is happening. They will just give you, okay, this might be a scenario where the fraud is happening. Go check. So this is the very first step that happens when before any machine learning model that needs to be built. Hence, EDA is the step, like the first step that I have always emphasized, right? And EDA also tells us, okay, what are the different transformations that can be done to identify any fraud, like, sorry, to get a better model performance. So I was using SageMaker Studio. So the question is, are you using AWS SageMaker for machine learning? I was using SageMaker Studio, but I did not use any feature of the cloud. I was just normally using a normal, plain, simple, vanilla Jupyter Lab environment, right? I haven't used any of the service as of yet, right? So I simply used it that because of the low computational power that my laptop has, right? So the different applications which are open already. So to keep the laptop fresh, like I just was working there. Okay, so Atharva Kande asks, how to decide which feature to drop by seeing the box plot, right? So see, box plot helps you understand the uh, distribution of a particular feature against the target column, right? So like you can plot it for any two features, but categorical and numerical feature, basically this box plot can be plotted, but to know how to drop a feature, it's basically, let's say a feature only has outliers. For example, in this particular notebook that we saw, so just a second, I will just let my notebook load. Yeah. So you can drop a feature based out of box plot when you see that there is no value addition to keep that feature there already. So for example, see this fetal movement. So for all normal, suspect, and pathological, it's just the outliers, but the majority of the value for all three of them, it's very near to zero, right? So it doesn't make sense to even keep fetal movement. So this is how you can like eliminate which feature to use, which feature to keep, like which feature to keep and which feature to like remove. So the tools that we are using right now are just plain simple Jupyter Lab. We are using Jupyter Lab environment, right? Which you can get from your Anaconda installation as well, right? So this is the Anaconda installation. Once you install Anaconda and you install this Jupyter Lab as well, you just click on launch. You would get started with something like this. Like it won't have different features which are there in cloud, but it will have the notebook would be running something like this. And you'd be able to execute it, select the, yes, do note, select the environment on which you'd want to start the Jupyter Lab on. So, right. So yeah, just do note that. We are, and for libraries that we are using, so I mostly stuck with Scikit-learn, Pandas, NumPy, Seaborn, Matplotlib. So Scikit-learn was for data splitting, or the algorithms which are there already implemented. Then Matplotlib, Seaborn, and they were for plots, all the plot that you're seeing. Then NumPy and Pandas are for data, in like to read the data, to transform, do any transformation. Yeah, on top of it. And please. Yeah, so I will be sharing this IPY notebooks as a GitHub file, which you guys would get uh, towards the end, right? what are the tools to run Python? Okay, Narayana Rao asks, what is the tool to run Python, Jupyter, or Python command prompt? So, tool is nothing but you install Anaconda and get this launch Jupyter Lab. So let me just launch it for you. I will just launch this. It will open it in my browser. So till this will take some time, but yeah, once you launch the Jupyter Lab, it will get started. Yeah. Yeah. So in GitHub, I will upload everything, the files as well as the Shreya Shetty asked, like, will we get the files and the data set to practice on? Yes, in the GitHub link, I will share the files as well as all the notebooks that I'm basically displaying. Purnesh Joshi asks, the decision tree is non-parametric. Is it necessary to make our data normally distributed? See, it's not 100, like it's not guaranteed that without even, like, usually what is observed is normally distributed features give a better model, like the model performs better on this. Even if the decision tree is not parametric, it totally depends on you. You can compare, okay, how it is differing, like whichever model is performing better, you at the end choose. But usually, normally it is fine. A normally distributed features performs the best. Okay, so Ankit Bhaviskar asked, how will we know, okay, what algorithm to use after seeing the data set, right? So see, I talked about supervised algorithms only. So let me just confine myself to supervised algorithm. So supervised algorithm take, okay, this is taking a lot of time, but okay. So in supervised algorithm, I specifically mentioned that whenever you have a labeled data set, right? And you can, so at that time only when you would be doing like sufficient labeled data set, only then you would be using supervised learning, right? Depending on the data, the target variable that you would want to predict, you would be using either classification or regression. So it would be classification when the target variable is categorical, but it would be regression if the target variable is continuous. So Akash Kanadi asks, how will we process the data in machine learning using AWS SageMaker services? So see, right now the session is about how to use machine learning, data science, like how to use data science skills on your local systems only. There would be a separate session on AWS services. So that's something separate, right? So here we are concentrating on the skills that are required, right? The things that you should be knowing before attending any interview or data science. So Akash Kanadi asks, is there any dependencies to use particular Dropbox? Not sure, but what the question means, but the dependencies are all covered in the the notebooks itself, right? So all you have to do is open the Jupyter Lab environment, which is taking time for me, but you open the notebooks, you install whatever the required libraries are, if in case they are missing, right? So let's say I'm using base root, right? Environment. So in Anaconda Navigator, you go to environment, you see, okay, what package I need to install. Let's say I want to need NumPy. Okay, I search NumPy and select the NumPy that I want to install and just double click on it to get it installed. Right. So that's how it is to install it, to install all the dependencies. Or you can even do pip install just like how I was doing, right? You just do pip install on the in the cell itself, and it will just install it for you. Siddhant Busari says, from problem, how should we decide ML algorithm? Okay. Crop, okay, like the problem is crop recommendation system. Okay, so this would come under collaborative filtering, right? Any recommendation system would come under collaborative filtering. This is nothing but a unsupervised problem, right? So we'll look into this. So as I said before, right now, whenever you have a sufficient labeled data set, you follow supervised algorithm, and depending on classification, like type of target variable, you do classification or regression. For recommendation systems, we will come to that, right? When the data set is labeled. What is fetal health? So fetal health is nothing but the unborn baby in the stomach of the mother, right? Womb of the mother. Purnesh Joshi asks, as dysentery is non-parametric. Okay, that we covered. We know that no type of plot is ideal for EDA process. Can I know the plot type that supports data learning and makes? So there is no simpler process. You have to get your, so the Kavya Badigar asks, there is no specific, no type of plot that is ideal for EDA process. Can I know the plot type that supports data learning and makes EDA process simpler? So the thing is, there is no simple solution for EDA process. You will have to get your hands dirty. You will have to plot everything. Like you'll have to ask questions to the data step by step, and only then that's like you would get the information or build proper models, right? Get successful as a data scientist. There's no simple process as such. Okay. So I think I guess there are no more questions. Are there any more in? Okay, what are the benefits of machine learning? Prajwal Riker, what are the benefits? Prajwal Riker says, what are the benefits for machine learning? See, you must have been hearing the news on ChatGPT and so on. So it's totally up to you to take the ride, which is the ride on the wave which is going on, right? To get better jobs, better salaries. So that's the one way to get out of like get benefited out of machine learning. The hype is there already, right? Suggestion function that we use. Kaggle is good place for getting started. Yeah, and GitHub link will be there, right? So what we'll do is we'll take a break. We'll just break up and start by 2, right? Get back on 2. Isnia, over to you.
Okay, sir. Hello.
Yeah.
So we'll be having a lunch break of 45 minutes. Will it do? Okay. We'll be having a break of 45 minutes. It will be a lunch break. So I request you all to please stay tuned. After 45 minutes, we will be resuming the session. Hello. Sushant, sir?
Yeah, sorry, I was speaking on mute. Let's just start back at 2, right?
Okay, no problem. Yes,
Yeah.
we'll be back at 2 p.m.
So we'll just resume it again by 2.
Yes.
But yeah.
Okay. So please stop sharing your screen so I can present.
Yes. Just give me a minute. Oh. Stop share. Yes, I have done that. Yeah. Now over to you.
Yes, sir. Hello, Sushant sir, are you there?
Yeah.
Okay. Shall we start?
Yeah, I'm good to start.
Okay, I welcome again all the students who are present in this workshop. And now I would like to tell Sushant sir to please proceed with the session.
Yeah, I'll just take over the screen. Okay, so in the first half, we talked mostly about just a second. Yeah, so in the first half, we talked mostly about supervised learning, right? We covered classification and regression. We looked at few examples. Now, we would be starting with unsupervised learning, right? So, unsupervised learning is where you only have input data and no corresponding output variables are present. Okay. In unsupervised learning, the models are trained with the data that is neither classified nor labeled. And the model acts on the data without any supervision. The goal of the unsupervised learning is to model the underlying structure or the distribution in the data in order to learn more about the data. In other words, the main aim of the unsupervised learning algorithms is to group or categorize the unsorted data sets according to the similarities or pattern or differences. Machines are instructed to find these hidden patterns from the input data. Just yeah. These are called unsupervised algorithm because unlike supervised learning, there is no correct answer to them. There is no teacher as such. Algorithms are left on their own devices to discover and present the interesting structure in the data. Unsupervised learning problems can be further grouped into clustering, association problems, and dimensionality reduction problems, right? So before I go ahead, like if you notice, like I haven't mentioned any, like unlike supervised learning, I haven't mentioned any training cycle or inference cycle. So because this is the model, basically the algorithm is working on the unlabeled data set. So it's unearthing the hidden structures or reducing the dimension of the unlabeled data so that it arrives at particular cluster or some association rules or reduced dimension. So there is no such thing called training phase or evaluate inference phase in unsupervised machine learning, right? So starting with the first type, the clustering, right? So the different problems which are there, the different types of unsupervised machine learning are firstly clustering, association node mining, and then dimensional reduction or embeddings, right? So first, let's start with clustering. What clustering is? Clustering is a problem where, yeah, clustering is a problem where you want to discover the inherent grouping in the data. It is the way to group the object into cluster such that the object with the most similarity remain in one group and the objects which have fewer to no similarities uh, are clustered in different clusters, different groups. So examples for clustering algorithms would be grouping of customers based on their purchasing behavior. Okay. Now, different algorithms that come under clustering are density-based clustering, then distribution-based clustering, then centroid-based clustering, then hierarchical-based clustering, We will check into few of them in our upcoming Jupyter notebooks. Then the other type is association. An association rule learning problem is where you'd want to discover rules that describe large portions of your data, such as people that buy X also tend to buy Y. In other words, the aim of this learning algorithm is to find dependency of one data item on another data item and map those variables according to accordingly so that it generates maximum profit. These type of algorithms are mainly applied in market basket analysis, web usage mining, continuous production, etc. Some of the popular algorithms for association rule learning are a priori algorithm, LCAT, ECLAT, FP growth algorithm, and others. Then finally, we have dimensionality reduction. So dimensionality reduction or reduction in dimension reduction is a transformation of the data from high dimension space to a low dimension space so that the low dimension space representation retains some meaningful properties of the original data, ideally which are very much close to the intrinsic dimension. So the dimensional reduction comes handy when let's say when the data is very sparse, or the data like you'd want to condense the information at a very small space, right? In very small space. So that is the time when dimensional reduction comes into play. So top 5 popular methods for dimension reduction are basically feature selection first. Second would be PCA, that is nothing but principal component analysis. Then we also have non-negative matrix factorization. Then there is LDA, linear discriminant analysis. And there is also another method called low variance filter. Right? Okay, advantages and disadvantages. Similar to supervised learning, unsupervised learning also has their corresponding advantages and disadvantages. Advantages would be these algorithms can be used for complicated tasks compared to the supervised one, because these algorithms work on unlabeled data sets, right? That is the very first thing. Then unsupervised algorithms are preferred over various tasks because getting unlabeled data set is much easier and cheaper as compared to getting their labeled counterpart. Then the disadvantages would be similar, right? Since we are working with unlabeled data set, the output of unsupervised algorithm can be less accurate, as the data set itself was not labeled from the beginning. And the algorithms are not trained with the exact output in the prior, like in when we are doing the training part, right? Working with unsupervised learning is more difficult as it works with unlabeled data sets that does not map with the output, right? So before we jump into the notebooks, few of the applications for unsupervised learning would be, first would be network analysis. Unsupervised learning is used for identifying plagiarism and copyright in document network analysis of text or scholarly articles. Then we also have recommendation systems. Recommendation systems widely use unsupervised learning techniques for building recommendations and applications for different websites and e-commerce. Then anomaly detection is another area where unsupervised learning is being used. Anomaly detection is a popular application of unsupervised learning where where they identify unusual data points within the data set. It is used to discover fraudulent transactions, basically anomalous transactions, or for predictive, like when you're doing predictive maintenance. So it's from the data points itself, from the uh, detecting fault even before the machine breakdowns, right? So those kind of anomaly detection can be done with supervised, unsupervised machine learning. Then we have singular value decomposition. SVD or singular value decomposition is used to extract particular information from the database. For example, extracting information of each user at a particular location, right? So that's where SVD would be used. Or it basically is a form of dimensionality reduction, right? Okay, before we move ahead, I will just quickly switch to the Jupyter notebook, right, to give you the examples. So very first, we'll just start with, we'll start with clustering algorithms, right? So as we have seen, like as we have seen, like in clustering algorithms, there are many different clustering algorithms, but then again, some of them are quite popular. So in this first notebook, we will just run a basic clustering algorithm on a small customer data set. Okay, so all the things that it have is, like, we'll be using k-means to find the clusters, right? Like discover clusters in the unlabeled data set, right? So first thing, we just run this. Okay, so we got data, loading the data set. The data set has just five columns. First is the customer ID, then we have gender, age, annual income, and spending score. Spending score is something that the shop has assigned based on spending pattern of the customer, right, for a particular customer. So what we do is we just run it, like I just load the data set in the memory with Pandas, right, with read CSV, and then I do information, like I just do data frame dot info to get how many null and what are the data types of the data set that I have, right? So yeah, so here the total number of rows that are there are basically 200, and none of them are null. So we won't have to do anything, like we don't have to create synthetic data or anything. All, like, apart from gender, all other data types, basically all other columns are of type integer. So that's also good. We just rename the annual income column and the spending score column to income and score respectively, right? And then we basically do some EDA, like, okay, what's the differentiation in between the customer ID? Like, usually what we would find is, uh, depending on the gender, that there would be different spending pattern. So we will just test that hypothesis out, right? So depend, like, for each customer, depending on the gender, what are the different plots which are there, right? So orange is female, blue is male. So depending on age, uh, there's not much difference as such. Like if you look at different plots, right, income and age, the plots is kind of mixed. So there is no grouping between the male or female, like depending on the gender, right? For age or income or score, right? So there is no differentiation as such. The plots look the same, like they are very similar as such if we look at it. So there's no so gender is there has no direct relationship to the segments of the customers. That's why we can drop this hypothesis and go ahead. So to first to find clusters among this particular mall data set, we'll have to know, okay, how many clusters can be formed, can even be formed in the data set that we have, right? So to do that, there is a method called elbow method, right? So what happens is, what you do is, depending on, we create k-means cluster for different clusters. So we start at 1 and go till 11, right? We calculate what is the intercluster distance, right? Intercluster distance and the intercluster and intracluster distance between between the clustering that we are doing, right? And we just plot that value. So the point at which this graph, so let me just bring the pointer. Okay. Oh, the pointer is not there. So so like when we plot this intercluster and intracluster the distances, like some of that distances on a chart, right? Depend on against the number of clusters as we increase the clusters, right? We see there are points, inflection points, where the graph, the slope of the graph changes, right? So at the start, it's pretty steep, right? When plus number of cluster was 1, it's steep. 2, it's steep. 3, it got changed, right? So this is one possible elbow point, right? So and then 4, nothing. 5, there something happened, right? At this point, right? The slope changed, and it was a bit drastic as such. At this point, the slope is pretty constant, but this is where the slope changed a bit, like a lot. So, and this is the other point. So these two are possible elbow points, right? So we will check, okay, whether number of clusters equals to 3 give us the better results, or number of clusters equals to 5 give us the better result, right? So this is how you arrive at the optimal. So I'm zooming the screen. Yeah, I hope the screen is visible better now, right? So this is one point where the like either 3 is the ideal number of clusters or 5 is the ideal number of clusters, right? So we will just check that what is the ideal number of clusters which are there for our use case. So what we do is we first create clusters with cluster number equals to 3, and then then plot the label, plot the clusters on the chart to see the differentiation, right? So we just do k-means, and as a parameter we pass it n clusters equals to 3, and just fit the data set. Once the data set is fixed, I do a plotting, right? So this is a plot of of the cluster that was formed. As you can see, like the green is 1 part 1, then blue is 1, the red is 1. In this thing, like in this particular format, still the cluster inertia, basically the intracluster and the intercluster distances are quite high, right? If you can see, particularly for cluster green, basically the green cluster, the intercluster distance is quite high for the points. So let's go with number of clusters equals to 5, and let's test how it looks like, right? So that's what we did. Just run this. And then these are how the clusters look like, right? So there is this the blue dots, cyan color, red color, purple, and pale green color, right? So this 5 clusters look much better as compared to 3 clusters. So going ahead, we'll just use with 5 clusters only. Okay. So score. Okay. So depend now these clusters, right? If we look at it, we plotted the score versus income and the cluster IDs, right? So if we look at this particular red cluster, so what we can feel is like the property for this red cluster is these are all low income groups. Like the people are all low income people, but they have very high spends, right? Hence this score is a high. Similarly, this purple people are low income and low spends. Because like let me just go back to what this score is. Score is nothing but the spending score, which was assigned to by the mall to each of the customer, based on their spending pattern. Okay. Now, yeah. So similarly, cyan color is like they have good income, like the income is good, and they also have like spending is also moderate, like they are not very high or very low, moderate. Now, if we look at this pale green, they have very high income, right? But their spending, the score is quite less. So that does make sense. So they have a low spending, high income, low spend. That's label number 3. 1 and then blue is nothing but high income, high spend. 3. Okay, so this naming got messed up, but yeah, due to like this naming was so what's happening is when we run this command, so these labels are assigned each time his label is different, right? So right now, the comments which were written here that are a bit wrong, but we can observe it from the graph itself. Blue is basically high income, high spend, right? So and understand the relationships with the help of graph, right? So let us check like for each of the cluster, what are the annual incomes specifically and what is the scoring specifically for them to get us more better insight, right? So the first chart is basically the different labels which are assigned and the incomes which are there, right? If we see for label 0, right, they have low income and the spends are also like all of them are very clustered, right? They're all of them are together. Similarly, same goes for label 4 as well. So they also have low income and label 4, the score is also low, right? But for label 0, income is low, but the score is high. So low income, high spend, and label 4 is basically like low income, low spend, right? This thing. Similarly, if you look at label 2, the income is moderate and the spend is also moderate. Okay. And looking at label 1, so they have high income, but their spending patterns are low and the score is low, right? So this is how basically you extract properties out of, like you use unsupervised algorithm, you group the data sets and then you plot it and see what are the different properties belonging to that group, and based on that you do task further down the stream. So we will check out a few examples later on, like how this grouping and properties would help. Like there is a popular concept called RFM, right? Recency frequency monitoring. So that's a market segmentation, like how to reach, like how to create segments of market to send coupons or any targeted marketing, how to do that. So RFM uses k-means to create the clusters and discover the segments, right? So we saw k-means. Let's check out agglomerative, like hierarchical clustering, specifically agglomerative clustering, right? So here as well, like we give 5 clusters. So linkage, as in it means the different criteria with which it should be measuring the distances between the cluster and intra and inter cluster distances. So there are certain fixed type for agglomerative clustering. So average is one of them. We'll just use this and fit and check out how the cluster look like, right? So if we check out this seems very much similar to the k-means with 5 clusters, right? One, two, three, four. Like it properly formed 5 clusters, so that's fine. This looks good. So this was one method. So there is another method as well, like dendrogram associated for like this. So there is this, like given this is a hierarchical clustering, it's done bottom top. Bottom of method. So it starts with the each of the nodes, then build up the map up. So that particular map looks like something like this, right? So what it is doing is it is finding nearby points, grouping them into one. So at first level one, what it did is it grouped 154 and 150, then 184 and 180. Similarly, going up, like similarly, it grouped a lot of these things. And depending on which clusters were closer, it grouped them into a particular cluster. And that's how it reached on the ideal number of, like, it stopped merging once it reached the ideal number of clusters that we defined, right? This we gave it 5, so it stopped merging when it reached 5 clusters. Right, so this is the dendrogram associated with hierarchical clustering. So previously, like this dendrogram, to create this dendrogram, we used the distance, the linkage parameter as complete, right? So let us check for what's the for average, how the dendrogram changes looks like, right? So depending on how the linkage is, so we change from average, like complete to average. So the top cluster change, like, right? So top cluster previously looked like this, 157. Now it basically looked like this. Red is the top cluster, then green and yellow, right? So that's how hierarchical clustering looks like, the dendrogram looks like. So depending on linkage, you change the method, like the behavior of the machine, of the algorithm to group. Then we have density-based clustering. So so for most of the traditional clustering techniques, like are either k-means, hierarchical, or fuzzy clustering. Uh, so they can be used to group the data without any supervision. However, like when we apply tasks, like when we are doing unsupervised algorithm on arbitrary shapes, right? Clusters, so something like cluster within cluster, or traditional like concentric circles, right? Right, something like that. So what happens is, at that point, the traditional approach for unsupervised machine learning fails, right? So it would not create good clusters. So in that sense, in for that instance, density-based clustering is what is used, right? So how it works is, density-based clustering I locates regions of high density that are separated from one another by a region of low density, right? So density in this context defines the number of points within a specific radius. Like, yeah. So for that, what we do is we just define it, like we just from sklearn cluster db scan, we just give it the minimum number of sample and the radius for which it should be looking for the points, right? For it to be named as a particular from a particular cluster, right? So we apply it on top of it, and if we look at it, we can see how the output changed. So clearly, this looks very bad. The red points are scattered all over. They're not in close. So this for this particular data set, DB scan is not the method to use. But depending on how the data is, DB scan is also something, is also one of those good algorithms which can help. So if we, so now plotting all of them in one place, k-means, agglomerative, and DB scan. If you look at it, k-means and agglomerative looks very much same, where k-means is bit better as compared to agglomerative, and DB scan is the worst, right? So this is how you, so this is how a normal unsupervised clustering is to be done, or is done, right? So we'll check out next example. Okay. So now that the notebook has loaded up, yeah. So the data set, so in this case, the data set that we are using is basically credit card data, right? For different customers, what are the balances for them, the credit card history for them, right? Is what we'll be looking into for this particular data set, right? We'll be checking out how dimensionality reduction can be used. How dimensionality reduction can be used to create the clusters, right? So first of all, we import bunch of libraries which are required, right? Pandas, NumPy for data manipulation, Seaborn, Matplotlib for for plotting all the plots. Then we have Sklearn. From matrices, we are using Silhouette score. So I will brief you on what this is particular score means in terms of clustering algorithms. So we'll just check that out, and then we just import k-means PCA for this particular notebook. Right? We'll just jump too quickly to layout score. So Silhouette coefficient or Silhouette score is a metric used to calculate the goodness of the cluster, goodness of the clustering technique, right? The value range goes from -1 to 1. This means like 1 means the clustering are well apart from each other and are clearly distinguished. 0 means clusters are indifferent, or when we or we can say that the distance between the clusters is not significant. And for Silhouette score, -1 means clusters are assigned in the totally wrong fashion. Right. So the formula, like if we look at the graph, right? So the formula for a Silhouette score would be looking like, let's say, if the distance between two clusters, cluster center is B, right? And the distance for intra-cluster is A, then the Silhouette score would be B minus A divided by max of AB, A or B, right? So that's the technical formula for Silhouette score coefficient. Going back to the credit card notebook. Yeah. So we just read the data set. Just a second. So what we do is we read the data set. And then we, like as usual, we find we look for some basic EDA before we move ahead and go do the final model building part. We check, okay, there are not some of them, like credit limit has one non-null, and then minimum payment has few of them which are non-null. So we will have to check what these particular null means in that particular column. But if you look at like the data types, customer ID is the only categorical feature. Rest of them are numerical. So if we look at it, credit limit has one entry which is null, and then minimum payment has 313 entries which are null. So how to get past that now? Like we will look into how we can replace these null values, right? So as we know, like customer IDs are something which are unique for every customer, so we can just drop it. Just a second. So for this particular notebook, what we'll do is we'll just fill up the null values with the mean for credit limit and the minimum payments. In the next notebook, we'll look at an intelligent way to refill this null values, right? Like replace the null values. So what we do is first we would need to, like, for each of the features which are there, we would need to identify first of all the outliers, right? For each of the numerical feature, what are the outliers? So we would have to identify them. Now to identify them, what we do is we use mean and standard deviation. So any value which is 3 standard deviations away from the mean, then we call that as an outlier, right? So what we do is we calculate mean values for all the numerical features which are there, and then we also calculate the standard deviation for each of the feature, and then we find out what is the 3 standard deviation from mean up and 3 standard deviation from the mean down, right? And then we calculate, like, once we calculate that, and after that we calculate the points which are actually outliers. So this is nothing but the data points, like the cutoff point for cutoff point which are like 3 standard deviations above the mean. Then these are the points which are cut off for 3 standard deviation below the mean. And then using these two at cutoff, we get these values as the outliers. And this is implemented in code as this, something like this. We get mean for each of the column, we get standard deviation. And what we do is we add 3 standard deviations to the mean values and subtract 3 standard deviation to the mean value, right? And then what we do is we do, okay, like we check, okay, what are the values which are greater than the upper limit and which are less than the lower limit, right? We just filter that and name that as outliers. What we do with outliers is we just straight away drop them because they are going to hurt our algorithm. Because they are outliers, they would be far from the clusters itself, and that would needlessly increase the cluster SMOTE score. So once we drop it, we check for once we drop the outliers, we check for the correlation among the features which is there. So the correlation as a heat map, if we look at it, we see -0.31 cash advance frequency with purchase frequency is the -1. But then in positive direction, purchases have a very high correlation with purchase transaction. Okay, that does make sense. And payment has a high correlation with purchases and one-off purchases as well. So we can see there are features which are pretty, like, which have high correlations with the other features, right? So what we do is now, instead of dropping the features, we condense all the information that is there with the help of PCA. Okay, so before PCA, we would want to know, okay, what is the ideal. So we would want to know, okay, what is the ideal number of clusters that this particular data should have. So we'll be just using SMOTE score for this particular use case. So what we do is we start from 2 and increase the value from till like till a particular limit. We fit the model and then calculate the SMOTE score, right? And as so this is the score calculation that was happening, right? From 2 to 26. Now, as we see, this particular score is decreasing. So number of clusters equals to 2 is the best choice that is there. So we just fix k equals to 2. And because there are so all of this data, it seems like all what we do is like with PCA, we also select the number of dimensions to which it should be reduced is to be 2, right? We just do that. We take the input data, we first standardize it, then apply PC on top of it, and on the output of PC is basically clustering is done, right? Once the clustering happens, we basically create like group this plot this cluster, and this is how basically the clustering looks like, the 2-dimensional. These are 2-dimensional because like this is the data, the PCA data, like post PCA data, which was fitted for k-means clustering, right? So this was basically use of dimensionality reduction together with clustering algorithm, right, to arrive at the correct cluster. Just a second. Now, next we will see few more algorithms which are there for doing this. Let's close this. Yeah. Yeah, so one more notebook for clustering, how clustering can be done, right? What all can be applied, how all can be done. So in the last notebook, we saw there were 2 clusters that can be formed on credit card data, right? So in this notebook as well, we'll be using the same credit card data set, but we'll be doing some like intelligent imputing, right, for the missing values. And we'll also be looking into different algorithms which are there for clustering for this particular data set. So at first, we import the basics, NumPy, Plotly, Plot9, then imputer from Scikit-learn, scalars from Scikit-learn, the dbScan, k-means, Gaussian mixture, right? All of the scores we first, like all of the libraries, we first import them. So once imported, so we then read the data set. So in the data set, we have for each customer ID, the balance amount left in their account to make the purchase, the balance frequency, how frequently basically the balance is updated. Basically, this would be score between 0 and 1, right? Then there is how many amount of purchases that has been made from the account, right? Some cash advance as well. Basically, the cash that was given, the purchase frequency, how frequently the goods and services are purchased on the credit card, right? So there are different columns depending on the different users for the credit card, like for the credit card information for each customer, right? So once we have that, we just do check, and we know there are some null values, so we just look for them. So credit limit has one null value and minimum payments has 313. So what we do is for to replace this one negative value, we think like first hypothesis would be because the credit limit does not exist for that particular customer, hence the value is null, right? So what we do is we'll check for cosine similarity of this particular user with the users who have high credit limit. Okay, so what we do is we write a function for to get the cosine similarity in degree, basically the degree for the cosine similarity. Then we fetch the object which has credit limit equals to null, and then from the top 5 we basically fetch top 5 entries after sorting it based on from the complete data set. We select top 5 entries after sorting the data set on credit limit, right? And then we calculate the cosine similar, the degree of cosine similarity between those the row which has missing credit limit and the remaining of the rows, like the top credit limits. Here what we observe is most of the values are nearing to 90 degree, right? So this says the entry is very much like basically the missing value is the row, that data point is very much similar to the top 5 entries. So what we do is we just basically replace the missing credit limit value with the mean credit limit of the complete data set. Okay, so basically what we did is we intelligently we tested a hypothesis whether whether the missing credit limit value is very high, or like what should be the value of it. Like we created a hypothesis that it must be a very high value. We tested it against cosine similarity for the top 5 credit limits, right? And when we found it to be true, we just appended the mean value in place of credit limit, right? Similarly, for the minimum payments, to check how to replace the minimum value, what we do is we look at the plot of it, right? Payments versus the minimum payments. We see that it is very much concentrated at this particular stage, right? So what we do is we log transform the minimum payments and the payment values to get a chart which is something like this, right? So what we do is next we then create. So we see that this is a very densely packed cluster, right? So this is just one cluster which is very much densely packed. So what we do is we just apply KNN imputer on the data set, right? On this log data set of minimum payments and payments after log transformation. So we just select the data, like we just select the data set first in this particular case, right? And just to avoid getting zeros, we add the small value and then do a log transform. right? So on this log transform data, we apply KNN imputer. So basically, what it would do is for any missing value, like from among the 313 missing values, for each of them, it would look at the five closest uh, value to this particular entry, to the missing value, and then this imputer basically would populate the missing value. Okay, so that is how we intelligently replace the missing values of missing payment, minimum payment, and credit limit. Right? Basically, after taking a look at the data. So after that, we check, okay, like if there, whether there are any more missing values. So since there are none, what we do is we then check for outliers. So we just wrote a function for the plotting, and then we plot all of it, like all we do box plot on all the columns which are there. So we see there are a lot of outliers in balance frequency, one of purchase frequency looks good. It does not have much of outliers, but one of purchase frequency is bad. Like it has some outliers. Same goes for these as well. So we basically notice that a lot of columns have outliers. So to use this, what we do is we will be applying Box-Cox transformation on this. Just a second. Yeah, so what we'll do is we'll transform the data transform each of these features with lot of outliers. With like the Box-Cox transformation would be used for frequency because of log, because it cannot handle negative values, and Ewan-Johnson's would be used for rest of the continuous data sets, right? Just a second, where is negative value? Purchases. Okay. So we basically create frequencies and the continuous data sets on which, like, frequencies would have Box-Cox transformation, and continuous values would be getting Ewan-Johnson transformation to remove the outliers, to basically remove and reduce the outliers. So that's what we did. We applied Ewan-Johnson and Box-Cox, both of them, and then we plot them again. So if we look at it now, the purchase has few, like it still has few, but it's considerably less. And rest of them also have considerably less. Frequency data. So what we do is, like, since they have considerably less number of outliers, we just use that for further processing. So we get that data, we append both the columns, right? Then we do some transformations on top of it. So this data set is not scaled at all. So what we do is we apply some robust scaler and standard scaler on the transform data. So we are doing this to identify, okay, which type of transformation would work best before we send the data for clustering. Okay, so first transformation is basically robust scale data. Another is basically the standard scale data set. So after transformation, what we do is we hmm, yeah. So after transformation, we apply like we write a function for PCA, right? To like basically to reduce the dimension of the to reduce the dimension of the data set that we have, right? So previously we saw, okay, two dimension works good as well. We just write the function to keep it handy, and then we write function for db scan, how to apply db scan on the data set that we have, right? So and then we basically plot, okay, how db scan would work for different scenarios. So what is happening is we we run db scan with standard scale data, right? And 10 as minimum sample, and the EPS to be zero point 0.8, basically the radius. So with that, what this is how the chart looks like. So if we see the red points are basically covering everything, right? It's very hard to make out even the rest of the points, the rest of the clusters. So this seems like a very bad thing, like very bad clustering algorithm. So if we check the bottom, so there is this is the similarity score. It is being printed, right? So this is in negative. So we like ideally we would want a highest similarity score to get proper clustering. So we just let go, like DB scan seems to be very bad fit for this particular data set. Then what we do is we check for elbow method. So to fix on the number of clusters that should be used, right? If we check this, three has a like when we use elbow method on robust scale data, right? This data which was robust scalar, on which the robust scalar was used, uh, we see that 3 and 4 are the possible elbows, right? 3 or 4. On standard scale data, we see the elbow might be around 5. 5 or 7, 7. Okay, so for elbow, sorry, for robust scalar dataset, we know exactly the elbow is at 3. So we just go with that. And for the standard scalar dataset, we try with cluster of size 7, right? So actually, like there is a very the slope is not abruptly changing anywhere. So that's why like we are just going with 7, but we could even use the value 5 because there is a slight elbow, like there's a change in the slope. So that's also looks fine. I would have to actually run this notebook to create that, but okay. Okay, let me try running it. Just a second. I'll just run this notebook. Just a moment. Okay, so data scaling, running it. Okay, so if we so on DB scan, if we just run it with robust scaler with the default parameters, right? So basically the minimum sample 2 and the radius of uh, density based scanning to be 17. So if we see that the clusters are found very badly, like this last one is overlapping a lot. So then if we look at standard scale data with the radius to be 2 and minimum samples to be 50, after so this is how basically the clustering look like, right? Which is much better as compared, but still it's not that good, right? And the silhouette score is quite less as well. So we'll just ignore that. So for robust scale data, with just 2 clusters, it still feels bad. Same for this particular DB scan. So DB scan seems to be a bad fit for this type of data set. Just ignore it. So for robust data, robust scale transformation, robust scale data, this 3 is the elbow, 3 or 4. We'll just check the elbow for standard scale data. So in this case, the slope is very small. So let me just select 5 because that is the value that I feel would be. So I use K and K means. So for robust scale, like because 3 is the default, so I'll just use default parameter. So this feels like a very better cluster as compared to the previous one. And let me check for 5 what happens with 5 for standard scale data set, how the cluster looks like. Okay, this is for 5 and this is for 7. I think this pink and red should be just one cluster itself. Shouldn't be like we can noise them. And then this should be part of this. Okay, I think 5 should be better. Yes, I'll go with 5. Right, 5 is much better, I think. So if we look at the silhouette score for transform robust scale data set, so we get a 0.99, which is very high, right? So this is so it's almost 1. Okay, so this is like almost 1. So this transformation and this particular clustering feels like the for us to go ahead with. So that is what we'll select, right? We'll then just check out agglomerative clustering for the same thing. We'll just check that once before we just finalize. So with transform robust data set 0.99, like we are getting good results. But for this standard scale data, the result, like the SMOTE score is quite bad. Like it's not as good compared, right? So then there is this Gaussian mixture clustering method as well, right? So what we'll do is like I'll just run this. So this is also giving us a very good result, right? Which is compared to 0.99. So these results are very good. So for this particular data set, DBscan performed bad, but robust scalar and transform data set, like we get a SMOTE score which is close to 1, basically 0.99, where the number of clusters are 3. So so coming back to the point, why clustering is required or why it is of use, right? So if we look at our examples, right, the first thing that we should be noting down is once we find the clusters, right, and after we plot them, we find characteristics of the cluster which are there, right? So for example, in our market data set, right, the mall customer data set, in a mall customer data set, like depending on like how different clusters were behaving, right? So we know this segmentation was able to be found, right? So this for purple, like this purple, like they are low income, low score. Then this red are basically low income, high score. Similarly, this pale green is basically high income, low score. Maybe like we found segments in the market, like in the customers of the mall. So let's say like if we offer any, so for these high income group people, high income and low score people, if we give them some offers, maybe they would convert more. Maybe the sale would increase, right? They already have the money, so why not? Like if we give them good offers, they would come to us, right? So this is how like depend like we extract the properties which are there for each of the cluster to find, okay, what should we be doing with the clustering method, right? Okay, I think there are a few questions in the chat. Agglomerative clustering method is the hierarchical clustering method, right? So this is we won't be going deep into the theory, but what happens is it works top down. So what I mean by top down is, just a second, yes. So this is basically the dendrogram, right? Okay, so for any clustering, distance is the like whatever formula that you use for distance dictates how the clustering would function, right? So in case of DBscan, we say, okay, like whether if there are a particular number of points in within the radius of it, will the new point will belong to that particular cluster, right? And that is how it is able to differentiate regions of high density versus regions of low density, right? So in agglomerative clustering, they use linkage, like there is a distance formula, right? Which where the linkages either can be complete or average, right? So depending on what the distance formula is being used, it finds like it at grassroots level, like when the individual points are there, right? So it would find, okay, what is the nearest point to 50, 51? So it says based on the linkage, like 51 closest point is 43, and then 68 to 65, they are closest, so we just group them. Now when they are considering this top, right? So when they are considering the group of 43 and 51 and 68 and 65, they see 45 is much closer to 51 and 43 group, so they group it. So that's how the bottom up grouping happens for agglomerative clustering. So these are this comes under hierarchical clustering. You might want to get to know more about the theory, you might want to read more about it. So Ranjana says, sir, can we say PCA is agnostic to Y? So PCA is done, is basically an unsupervised method. So there is no target variable as such. And then K-means, Akshay Kanade says K-means is most widely used centroid-based clustering algorithms. Centroid-based clustering algorithms are efficient but sensitive initial condition and outliers. Yes, that is true, Akshay. Akash. Hence, we like, because they are sensitive, like at the end of the day, all clustering algorithms are using some one or other kind of distance measuring metric, right? So specifically for k-means, that particular measure, right? So what we get calculating L2 distance, right? So that particular measure is sensitive to the outliers and where the initial point start with. Hence, we first remove the outliers to get better, to start at a better starting point. So this is Ranjana says what is the code editor. So this is nothing but a Jupyter Lab environment that you would be using Anaconda. So I just Akshay Akash Kanade says ask what are the use cases of clustering. So we just discuss, like I just explained, okay, how the clustering can be used. Like we, after clustering, we find out the properties for each of the cluster and then use it for further down the line for marketing purposes or any other purpose. Like marketing is one use case, but there are multiple such use cases, which includes recommendation as well, right? Recommendation comes as part of association rule mining. So we'll be checking that out next. Can Akash Kanades ask, can time complexity applications achieve k-means this? See, for k-means, the total time complexity is of the order n cube. Just a second. Yeah, so the time complexity is of the order n cube. So, because the inherent nature of the clustering, right? So this is happening because each time we are finding a cluster, right? So what is happening is each number is measured against, like each entry data point is measured against the all the other data points, and this happens for all of them to get, okay, which data point is closest to which particular point. And hence k means, like these clustering algorithms usually take a lot of time, and they are very the time complexity is quite high. So Diksha Kohli asks, can you provide software description for Anaconda? So for your local systems, you would be just installing Anaconda to get started with Python and the Jupyter Lab environment, right? Once you install Anaconda from Anaconda Navigator, you would be getting Jupyter Lab and the virtual environments, and with that you would be getting started, right? Okay, so now that clustering is done, we'll switch to association rule mining, right? Just a second. So association rule mining, right? So how to get started with that? So like why it's of use, and like and where it's basically used. So association rules are basically, right. So people who buy, like you must have seen in Amazon, like Amazon or any or any e-commerce site, when you're buying something, towards the end, right, you also get the notification of people also buy X. Like once, if let's say something, milk is in your uh, basket, then it says, okay, people also buy bread, right? So people also buy bread together with milk, or let's say they also buy honey, or some kind of rules like this. So at times what happens is, when you see the arrangement of shelves in the supermarket, they can also be arranged with the help of a priori, like association rule mining. So depending on what people buy together a lot, right, you can arrange these shelves such that the things which are to be bought, which people buy together frequently, can be grouped together, right? Or they can even be placed to increase their marketing. They can just place these things far away from each other, so that the customer would be going through the complete mall and increasing the time he spends looking at the products, and maybe he would change the mind and hence buy more, right? So depending on what the objective is, association rules can be used. So going ahead, like how this how what the code looks like, right? So in this particular thing, we will be using an open source grocery data set, right, which has about 38,765 rows and 3 columns. So the data set is basically nothing but, okay, which member on what date by what bought what thing, what particular thing. So we'll just restart and just, so we get for each member the date he made the purchase of a particular item, right? And then if we look at the total number of items sold per day, like by the date, right? So this is how the chart looks like. So it looks messy, but you can see like so there is a pattern, right? So it's going up and then it's coming down, right? So it's kind of alternating in sense, right? So there is some seasonality. So what we do is we will set date as the index, right? And now what we'll want to do is, so what are the total unique items? We'll calculate, okay, what are the total unique items that were sold? We'll also see, check out total items that were sold throughout the year, with average of and the total average of items that were sold per day, right? So we see that like 160, there were total 167 unique items, and in 12 these total of 38,767 items were sold in 278 days, right? So if we plot this chart by date, right, by month, items, date. So this is how basically the chart looks like, right? So this is cleaned and we aggregated it for on a date level, and hence it looks pretty neat. So if we aggregate the data further on a monthly level, so we see, okay, this is how the chart looks like. So we see that there is a trend and which is increasing, right? Okay, so then what we do is like for each of the items we say, okay, what whether it was a weekday and what was the hour when the sale was made, right? We just calculate some additional features, right, out of the date. Yeah. So for date, there are 278 total unique impressions. And then we plot for bar, like we plot a bar chart on different item. The basically the histogram bar plot. Okay. Yeah. So for each of the items which were sold, right? So what was the count of each? So that's what we will just see. So we see like the count of each of the thing that was sold, right? So there is the list is quite long. Like this is like a very skewed data set. But yeah, so that's how usually this basket analysis would be going for, right? So what we do next is per member, how we'll check. Okay, what was the for each member when he made what purchases, right? So to calculate the a priori rules. So for member number 1000, he made purchases on 5 different dates, and he bought sausage, whole milk, semi-finished, bread, yogurt, milk pastry, salty snack, so and so on. So like he bought a lot of different things, right? So similarly, we group them for each of the member level. So what we do next is basically we look at only for the transactions, right? So what all things that were bought by different like what all things that were bought together, right? To calculate the association rules. So for right. So what we do is like we just list out the transactions, right? So in this case, tropical fruit, soda, yogurt, root vegetables, yogurt, domestic eggs, white wine, a photo film were bought together, right? So we'll check, okay, whether tropical fruits are bought together with yogurt a lot or not. What would be the support for this? What would be the confidence for this? Right? We'll be calculating these two values for each of the pair of the item, right? Okay. So what I do is I use transactional encoder from ML extent, and with that I basically encode all the transaction which were there. Basically, all the this complete list I basically just encode that. So it basically says it's a very sparse matrix where the items that were bought together are one, like basically are true, else they are false. So if we want to take a look, this is how it looks like. Describe here. So just a second. I do head. So see for whether which all were bought together would be one if they are bought together, else they would be zero. Sorry, if they are bought together, they would be true, else they would be zero. 167. There are just two entries for true or false. then we just plot some things to just check, okay, what the distribution is looking like, how the count is, and so on. Now, what we do is we create a word cloud. So depending on how many items, like whole milk was bought how many times, so to make it pleasant, the size of the words, to create basically a word cloud to understand, okay, what items are being used more, the size will, depending on this count, the size of the text would be larger, right? So that's the word cloud. So if I just run this, I will get this particular word cloud, right? So vegetable was brought a lot, milk, then fruits are being brought a lot, beverages. So name, this seems to be some small item. Brown items seems to be some small items which are bought in small quantity. So then there is this other pre-map as well. So there is this other graph which talks about, okay, the distribution. So this is other way to look at the chart. So now finally to calculate the support and confidence, we from ML extend, we just use priority and association rules. Then in a priori, we just give it the give all the transaction. Then we also give the minimum support and whether to use the column or not. So minimum support is basically like whether a particular grouping should be done or not. What should be the minimum support for that? Right? So we calculate that and then so on continuing. So what we get at the end is basically, let's say if a person buys bottled water, then next he would be buying a milk, will have support of 0.06. Sorry, it will have the support of 0.02 and confidence would be of 0.017. Right, so this particular rule, complete rule, has the support of 0.001 and confidence of 0.01. Right, so it has a list of these rules are there, like depending on what things are brought together, the confidence and support would be high depending on those things, right? So I would not go into the details of what are the formula for support, confidence, lift, and what all thing antecedent support, consequent support means. But if interested, please go ahead and check that out as well. So what I will do next is basically I'll just plot these things, these rules. So basically the distribution of confidence and the support over the values. So there are a few which are high values. Because it's kind of concentrated, I will plot a log, I think. Support log. Victim confidence. Yeah, so this is how basically the association rules are calculated, right? The confidence and support values are calculated, and based on support and confidence values, you use, okay, like you basically group, okay, what items should be bought together, right? That kind of recommendation is given. So this is one. So this is one use of association rule. So next would be how to use that for marketing. So I will be using the same data set. I use the same data set, right? I get member ID, date, and item name. So from that, what I would be doing is I will just first create visualization which are similar, right? So depending like how are the sales, weekly sales going on, right? So depending on customers, like total customers which are visiting weekly, right? So there are different graphs which are there. So sales per customer which are happening per like every week, right? So then we also check out the frequency of the items which are sold. Details. Okay. Oh, wait. This. So it talks about different like this artificial sweetener label. So it was sold 29 times, right? So that is the detail. Oh. Yeah. So now what we'll do is we'll just check, okay, who was the top customer based on the number of items that he bought. So we see, okay, this 3180 is the best customer because he bought like 36 different items, right? And if you look at the 20th top, he bought around 27 different items, right? So these seems like a top customer for us. Then number of sales per discrete weekdays, right? So what was the like each weekday, like what are the different sale figures, right? Cumulative. So that's what we get, like that's what we plotted, right? So for different months, what are the sales figures? So these are the sales figures for different month dates, right? These are per date. So if you look at it on 31st, seems like everybody is having the cash crunch, so they don't go shopping. Like the sale is like quite dropped as compared to the rest of the days, right? So like we plotted these things to basically it helps us understand okay, what's happening with the data, right? What is the consumer behavior? So maybe let's say like if you know this is the behavior on 31st, we might keep scheduled maintenances, right? Or restocking, like some restocking, cleaning of the warehouse and so on, right? So that is how that can be planned in. Now to do market basket analysis, what we will do is we'll first create baskets out of the items, uh, like for each of the user and the item, what is the number of time the basically the item was bought. Like if the person bought that particular item, it would be 1, else 0. So this particular this basket data frame would be very sparse. It will have a lot of zeros and very few ones. If you look at it, the total number of times this milk was bought by all the customers is like 2502. And then what we do is we one hot encode them, these basket values. So once one hot encoding is done, we create a priori. Basically, it gives us, okay, what for each of the two items, what is the support, and then we calculate the association rules. So for each item, like if sausage is bought, then then yogurt would be bought with a particular support and particular confidence, right? So that is basically given here. So this is particularly for doing market basket analysis. Now let's check out a different use case of RFM analysis. Basically, that's recency, frequency, and monitoring. Right? How these how basically market segments can be formed out of the data that we already have, right? To do some targeted marketing. So what we do is to calculate recency, we just need to know, okay, what was the most recent date, like from the current date, this which customer bought most recently, like, right? So for each of them, we calculate, okay, what is the most recent date the particular customer bought. So what we are doing here is we calculate the maximum date that is there in the complete data set, and then we subtract the last bought date for each of the customer with that, and that basically gives us the last bought date for that particular customer. So for customer ID 1000, he bought 35 days before the last date of the data set, right? Similarly, 1001 bought 260 days before the last bought date, right? And so on. So this becomes the recency column. So if we look at it, the recency distribution looks like this, right? So this is also a very long-tailed distribution, skewed, right? And majority of the weight is just between this 150 to like 300. So that's where the majority of the weight is basically there, and outliers are post 600, right? 600 value. The outliers are basically present. Right. So okay. So as you can see, the median is at 139. The first quantile is at 57, and the third quantile is at 280. So between 57 to 280, that is there. That's where the maximum number of people have bought, right? Their last bought date was. Now after this, we'll calculate, like we got recency column. We calculate the frequency column. So how frequently a particular member bought from the mall. So what we just have to do is, like, we just calculate the total number of purchases he did, right, on different dates, and we just count them. So we just get the frequency, the total number of times the member 1000 bought was 5, and so on. So this is the particular chart for that, and the most of the weight for the graph is basically between 2 and 5. So most of the customers bought at least twice and at most 5 times. Most of the customers, 50% of the customers. And then once that is done, we calculate the monetary value, right? So what we do is, so in this case, because the price was not given, what we assume is each item is of equal price. I understand this doesn't make sense, but for the sake of it, for the sake of understanding, like what we'll do is we'll assume each item is of price 10, and depending on the total items that he had bought, we just multiply it to get the monetary value, right? So so the distribution looks like this on the plot, right? And now what we do is we concatenate recency, frequency, and monetary value for all the customers, right? And we get something like this. So for each member, we get what was his last purchase date, like how many days before he bought, how many times he bought, and what was the monetary expenditure he made, right? So based on this, what we do is we calculate buckets out of it, right? Quantile buckets, and we get RFM scores. So what we do is we are doing some bucketing, right? We are giving it 1 to 5 buckets for recency, frequency, and monetary. And once out of the bucket, depending on, we just give, like we observe, okay, let's say if a person, for this particular use case, the visit frequency was 5, the recency quantile was 5, and the frequency was 4. So this guy is like a very regular, this looks like a very regular customer for us, for the business. Hence, he has been classified as champion, right? But let's say, let's look at the other guy, 1001, right? His frequency was 5. Oh, wait. Visit frequency is 5. Recency quantile is 2. So it's been a long time he visited the basically the store, and his this monetary, just a second, his monetary purchases were also high, right? So it's like, it's been very long time that he has been to the store, and let's say if we give him order, like give him an offer, maybe he would come back, right? So right now he's at risk. Hence, like we created some rules. Okay, let's say depending on which bucket, like depending on what quantile or bucketing this recency, frequency, and monetary values are, we assign it a group, and this is how the champions look like. So like basically the overall chart, the customers look like the segments. So if you look at it, there are 1005 hibernating customers, right? So which are like 26% of it. So there are 390 champions. So for 390 champions, all the monetary, recency, and frequency values would be high. At risk customer are the one who are very likely, like they haven't visited the store for a long time, and you would want to target them to bring them back to our store, right? Similarly, for the rest of them, the definitions are there. So this is how you basically use RFM, like agglomerative clustering, or basically, sorry, the association rules to calculate RFM as well, right? To understand like how unsupervised learning can help you do market segmentation and market analysis, right? So there are softwares which are doing this, and they are very costly, right? So they are doing just this same exact thing, but they charge their end users a lot. So this is what goes underneath. Okay. So I'll just skip this. Okay, semi-supervised, right? So I'll just come back to the slides. So semi-supervised learning. Semi-supervised learning is a type of machine learning algorithm that lies between supervised and unsupervised machine learning. It basically represents the intermediate ground between supervised with labeled data, labeled training data, and unsupervised learning with no labeled training data. So, and it basically uses the combination of labeled and unlabeled data set during the training period. Although semi-supervised learning is in the middle ground between supervised and unsupervised learning and operates on the data that consists of few labels, it mostly consists of unlabeled data. As the labels are costly, but for corporate purposes, they may have few labels. And it is completely different from supervised and unsupervised learning, as they are based on the presence and absence of the labels. So that this is how the semi-supervised learning is differentiated, right? So it uses small portion of labeled data as well as unlabeled data for its training procedure. right? And like when, let's say, like supervised basically consists of doing training when there is labeled data set present. Unsupervised, unlabeled data set is present. And this semi-supervised is like the middle ground between both of them. Now to basically semi-supervised came into being to overcome the drawbacks which were there for both supervised and unsupervised algorithm. The main aim of semi-supervised learning is to effectively use all the available data rather than only labeled data like in supervised learning. Initially, similar data is clustered with unsupervised learning algorithm, and further it helps. Like initially, with the labeled data set, you train initially with the labeled data set, you train a basic classifier, and then using unsupervised learning, they use the similar they find out the clusters of similar data points, and based on those clusters, they propagate those labels to the unlabeled data set as well, right? So semi-supervised, the self-training method that you see on the slide is what happens is, like, you pick a small amount of labeled data. It can be images which would be showing cats and dogs and with their respective tags and so on. So, and you use this data set to train basically a base model, right? With the help of ordinary supervised methods. What happens is, like, after you train this first base model, you then take this labeled data set is very small, right? So do remember that. So you take a lot of the unlabeled data that is there, you make it pass through the base model that you just trained, right? And then you get pseudo labels. So these labels would be good, would not be good. So some would be very good, like so these labels are called pseudo labels, and some would have very good confidence, but then some would be very bad, right? So what you will do is, you will take the labels for which you have high confidence. You take that, you take the small portion of the originally labeled data set, right? Together with that, you create the new data set and train a new model, get the predictions, and repeat the procedure. And this is how you basically improve upon your model for the semi-supervised learning. So basically, you would be getting so the first question would be the model that you train with the small label data set, the pseudo labels that you obtain, like what should be the threshold. So you can keep a threshold of, let's say, 80% probability, right? So with that, with something like that, you can, like, iteratively improve upon the amount of data that is labeled, and as well as you would get better and better model every time. So provided that the data is suitable for this purpose, the performance, like with this, after following this method, the performance would keep on increasing in each iteration, while while there are successful examples for self-training method, it should be noted that the performance might vary from one data set to another, and there are plenty of evidences, right, where self-training may even decrease the performance as compared to taking only the supervised route. By the way, ChatGPT and other advanced LLM are all semi-supervised. So coming to the advantages and disadvantages. So advantages would be, it is like semi-supervised. It's very simple and easy to understand. The algorithms are very easy to understand, and they are highly efficient. they are used to solve basically the drawbacks which are there in supervised and unsupervised learning algorithms, right? But on the other hand, disadvantage would be the iteration results may not be stable, and then you cannot apply these algorithms to network level data, and then accuracy might even be low. Even after doing all the fine tuning processing, the even at the end, the accuracy might still be very low, right? So we'll just quickly check out an example for semi-supervised. Okay, so the example that we're going to be checking out is basically a Twitter emotion classification. This is a NLP task, right? In this case, in this particular case, we'll be using embeddings, right? So supervised, semi-supervised learning, right? We would have to use, like as we said out before, right? So we would have to use something which is already trained on a particular data set, right? And then we'll be using that as a subroutine for our training to create the new classifier model. So what we'll do is we'll just load this. So I loaded the training, test, and validation data set, right? So the data set that I have is like, I didn't feel like humiliated. I can go from feeling so hopeless to so damn hopeful just for being around someone who cares and is awake. So there are different sentiments associated with each of the tweets that are going on, right? So we what we do is like we just read the data set with using the pandas, and then we basically map them to the different classes which are there, right? So the different classes are sadness, joy, love, anger, fear, surprise, right? So we just map them. Now we do some pre-processing on top of it. So there are different pre-processing for NLP related tasks. There are different pre-processings that can happen, that can go in hand with these, right? So what we do is like we first check out, okay, what are the texts and what are the corresponding labels associated with it, right? So I'm feeling grouchy, so label number 3, right? So we add these to the data set, that the data frame that we have, right? So the 3 maps to anger. I'm grabbing a minute to post. I feel greedy wrong. So this is mapped to anger as well. So and so on. So these labels are mapped. Now we check out, okay, what is the distribution of each of the labels? So if we see surprise is the least, love, fear, anger are kind of less. They are not that high. But then sadness and joy are the two which are dominating all the rest of the categories, right? And then we check, okay, what is the length of average length of for each of the tweet that is happening, right, for different classes. So we see all of them minimum has 2 or 3 words, right? If you see, all of them are like quite similar, just that all of them have a long, like pretty good, like good amount of outliers as well. So what happens is, like, we cannot, like, the machine would not understand text, like characters as it is. So we would have to embed them, right? So there are different ways for doing embeddings, right? So the first of those is basically character. So before you embed, you'll be doing tokenization, right? So to character tokenization would be like each letter is broken independently, right? So if you look at this list, if you look at this list, so each letter is broken into independent string and we get such tokens, right? And then from tokens, you calculate the length of vocabulary. Okay, so how many times F occurred in this complete list of tokens? That was 9, right? So you calculate the vocabulary, and this is reconstructing text is like pretty hard, right? So like you can imagine like this if, you can imagine like this would make any matrix very sparse matrix, right? So it's so there are certain drawbacks which are associated to character tokenization. So character tokenization ignores any structure in the text or treats the whole string as a stream of characters. So this deals with misspellings and rare words, but the main drawback is that in linguistic structures need to be learned from the data, right? So even if character tokenization would help deal with the misspellings and everything, but in any text, like in any spoken language or any sentence, linguistic structure is something that needs to be learned from the data, and hence character tokenization is rarely used in practice. Instead, to preserve the structure, the linguistic structure, we use word tokenization for NLP, right? So what happens is word tokenization, it is broken after every punctuation or space, right? So if you look at this, tokenization of text is so these are like independent words. You just broken off at spaces. So what we'll do next is basically we'll use from these tokenization, like from these texts, like word tokenizer. This was one way of tokenizing, but then there are advanced methods as well, right? So there is BERT, there is distill BERT, right? So which can help with this tokenization, basically creating the embeddings, right? So what we'll do is we'll just use distill BERT to create our tokenizer. So that's what we did, right? So we create a tokenizer using distill BERT model, so which is available in PyTorch, right? Basically Hugging Face in Hugging Face library. So what we do is we check out, okay, what is the max vocabulary size of the tokenizer? What is the max length of tokenizer, right? We do that. We then convert all the encoded text that we had, right, into the tokens, right? So after converting it into tokens, right, the complete data set into tokens, so we get where did it go? Okay. So after creating tokens out of the complete data set, we are basically ready to go, like create, like use that as a subroutine in our fine tuning, like in our text classification, like sentiment classification, right? So in this case, what happened is we use a tokenizer. This is a text, right? And then we use that model, give it as an input to the model, right? And then just process the output, right? And because like we haven't given it the, like for the tokenizer, we haven't given the last layer, right? We haven't given, okay, how the classification needs to be done, right? In the 7 different categories or the emotion categories, right? Love, anger, hate, and so on. So we just replace that and do some training. We create this feature matrix and everything. That's fine. Just a second. Set format. So what we are doing is basically in this auto model, like from the pre-trained model itself, we take the model, and in this model we use that to get the output, right? And then we map the output to our classification, right? At this particular stage. So we get the output for each of the inputs that we send, right? We get something like this. And then what we do is basically for the complete feature matrix, right? For the complete training data set, what we are going to be doing is we'll be first visualizing how the training data set looks like. So what we do is we reduce it to visualize this training data, like each array is of like one, two, like it has multiple dimensions, like 768 dimension, right? So that we first dimensionally reduce to 2 and then plot as a scatter plot. So this is how the embeddings look like. Yeah, this is how the embeddings look like. So for joy, it's very much centered around 0, right? If you see, this is like centered around 0. But for surprise, it's like very sparse. And fear, it's getting a bit denser. Then anger is again denser than fear. But fear and anger are kind of similar looking, right? Then love and joy, the center is quite crowded, but for love, the outer regions are quite sparse. But then if you look at sadness, if you see, the outer regions are dense, but the center region is kind of devoid, right? It's sparse, right? So you can see like there is a relationship, right? The tokenizer, the embedding that we use did some like the linguistic structure was kind of preserved, right? So with those embeddings, right, with these embeddings, what we do next is basically we train a model, right? So we just create a small classifier, we give the embeddings as a training, and just we create a training, right? So a dummy classifier gives us a 35% accuracy. Then logistic regression gives us a 63% accuracy. And if we look at the the confusion matrix, right? So we can see that anger, fear, and surprise are often confused with sadness. 0.67. And love and surprise are frequently surprise. Okay, love and surprise. So all in all, that this particular statement is wanting to say is what we can see from the confusion matrix is that fear, surprise, love, they have like they are very near to each other. Like on the sadness part, like they are very the confusion matrix. It's making error. The classification that the model that we use, it's making error for these three categories, right? Similarly, for others as well, joy and love as well, it's making error. Joy and sadness and surprise, kind of very much similar for joy, right? So it's making error. So what we can do is like we can even fine tune this tokenizer. We can fine tune the embeddings that we have to get better intermediate embeddings, and we can even use better models to get to better results as well, right? So if we look at this, so we trained a transformer model. So instead of using small models, we trained the transformer models with the same training data, and we were able to get like FN score of like 90 to 93%, right? So which are very good as compared to the previous results, right? If we look at it, right? So this graph looks very good now, right? The anger is being classified for anger only, right? It's not being mistaken for any other category, and so on. So that is all. I think in the interest of time, I will just stop here for the semi-supervised. But that is all there for semi-supervised machine learning, right? So next topic would be, yeah, to help you understand what embeddings are, right? So that was a bit heavy, and it gets hard to understand, okay, even relate on how embeddings would look like. So as a definition, embedding is basically a relatively low dimensional space into which you can translate a high dimensional vector. Okay, so you are basically bringing a high dimensional vector like an audio file or a complete text file or a video file into a series of list of numbers, right? So as you can see here, audio file with or some audio module, you convert it into some embedding. Same for text and video. So that can be done, right? So embeddings makes it easier to do machine learning on large input like sparse vector, which represents the words. Ideally, embedding capture some of these semantics of the input by placing semantically similar inputs closer to each other. So what I mean by that is, let's say when you look at this, right, king and man. So both of them are male. So what you would do is like if you from king you subtract man and add woman, then you would be getting queen. Okay, so this is how embeddings look like. So basically, the embedding for the word king encapsulated the meaning, like it is male, it is a king. So equivalently, let's say from uh, king is basically male ruler, right? So if I subtract male part out of it and add a female counterpart, so I would get queen. So that's how embedding works, right? So semantically similar words are placed closer as compared to semantically different words. So let's say in sense of verbal sense, then walking and walked, swimming and swam will be on the same distance from each other because they are present and past participle of the words, right? Similarly, the relationships between Spain, Madrid, Italy, Rome, Germany, Berlin, Turkey, Ankara, right? Russia, Moscow. So these relationships are also preserved in embeddings, right? When you create embedding for that particular purpose, these kind of relationships are also preserved, right? Hope that help you understand embeddings a bit, right? But embeddings is a very powerful concept which is often used in machine learning domain. And as you have seen, like how ChatGPT is making waves and different, there is this race of larger and larger language models, right, which is going on, which has been gone off. So embeddings are the thing that are being used. Okay, there are no questions as such. Okay, now, so coming to reinforcement learning. Reinforcement learning is a type of machine learning technique that enables agent to learn in an interactive environment by trial and error, using the feedback from its own actions and experiences. So though both supervised and reinforcement learning uses mapping between input and output, unlike supervised learning, where the feedback to the agent is basically correct set of actions for performing a task, reinforcement learning uses reward and punishment as a signal for positive and negative behavior. So for each action that the agent takes, right? So environment would be giving out the corresponding reward, and it would go into a particular state, right? So next action of the agent would be dictated by the reward and the state which the environment gave to him, right? And the cycle continues. For the agent, it looks to optimize on the reward part, right? So it can be either minimize the loss of reward, or basically optimize the maximum reward that it can gain at the end, right? So that's how this reinforcement learning works. So, but when you compare it with unsupervised learning, reinforcement learning is different in terms of goal. Well, the goal of unsupervised learning is to find similarities and differences between the data points, right? In case of reinforcement learning, the goal is to basically find suitable action that would basically maximize the total cumulative reward that the agent would be getting, right? That I just explained. So this particular diagram illustrates that cycle of action and reward, how it goes. This particular diagram is basically a Markov decision process. Short form, shortly, it can be called as MDP. It is basically used to formalize. MDP is used to formalize reinforcement learning problems, right? So if the environment is completely, let's say, like whenever the environment is completely observable, then its dynamics can be modeled as a Markov process. And in MDP, the agent constantly interacts with the environment and performs actions. And at each action, the environment would go from one state to the new state and would also give out reward to the agent. Now, there are typically two types of reinforcement learning, which are like positive or negative, right? So similarly, like this reward can be either positive or negative, right? It totally depends on the action that was taken. And the agent learns what action not to do based on the reward which it obtains. So the goals of positive and negative reinforcement, though they are same, how they achieve it is a bit different. So positive reinforcement learning means adding something to increase the tendency that is expected, that the expected behavior would occur again, right? So it basically, like any positive action is basically rewarded so that the same behavior would happen again. So it impacts positively on the behavior of the agent and increases the strength of the behavior, right? This particular type of reinforcement can sustain changes for a long time, but too much of positive reinforcement may lead to like an overload of states that can reduce the consequences. Basically, let's say if you are giving out a lot of positive reward, then and not enough negative rewards, then what would happen is the agent would basically slow down. It would not optimize further. right? And then negative reinforcement learning is basically the opposite of positive reinforcement. As it increases the tendency that the specific behavior will occur again by avoiding the negative condition. So negative reinforcement can be more effective than positive reinforcement depending on the situation and behavior, but it basically provides reinforcement only to meet the minimum behavior. Okay. So there are two popular there are two main popular model-free reinforcement learning algorithms, which are basically Q-learning and SARSA. SARSA stands for State Action Reward State Action, right? They are two commonly used model-free reinforcement learning algorithms. They differ in the terms of their exploration strategies, while exploitation strategies for both of them are same. Oh, okay. So I will just quickly show you an example of reinforcement learning. So what I did is basically I got a Sudoku dataset, right? And then I created the environment, like the agent, right? This particular agent. So I created an agent and an environment for solving Sudoku. So this Sudoku CSV has list of different games which are there. So what happens is my agent basically solved this game.solve, right? So solve is the agent which basically tries to solve the Sudoku, and then it compares against the environment, and based on whether the Sudoku was solved properly or not, the reward is basically given, right? So what's happening is like I made it go over like 10 million times, like 1 million times. So I made the agent go over this game for 1 million times, and out of 1 million times, 97.4497% this particular agent worked correctly, right? And it worked correctly. So like so as you can understand, right? So what happens is like looking at the Sudoku game from the perspective of this particular angle, right? So what is happening is each time a game starts, the agent solves the Sudoku, tries to solve the Sudoku. It then sends it to the environment to evaluate it. Depending on the evaluation, whatever the evaluation is, right, whether the Sudoku is right or wrong, it would go to a different state and as well as send a reward, right, to the agent. Now, based on the reward, agent either improves or let's say like if the reward is positive, then the agent would improve and keep on doing the same action again. But let's say if the reward is negative for the wrong Sudoku, then agent would try to avoid the action that it did last time, right? To basically optimize on the reward. And this procedure continues till like basically I ran it for 1 million times, and within 1 million times it got the Sudoku correct. Like the agent was improved and got the Sudoku correct for 97.5%, right? So this is how basically the reinforcement learning problems look like, right? So this was a very simple problem, right? So in this case, not much was done, but let's say there are advanced versions of Q-learning or SARSA as well, like DQN and so on. So depending on the use case, you'd want to use reinforcement learning as well. So for example, in industry where this can be used is like, let's say for optimization, there is a problem called vehicle routing problem, right? So which route a particular vehicle should be taking to optimize on a particular criteria, maybe time or money or petrol or anything else, right? So that it covers the complete area, like given nodes that were assigned to it, right? So in this particular case, agent, like we can have a reinforcement learning agent try on this different routes and reach on the optimum strategy to select what how the route for a particular day should be looking like, right? Okay, coming back to the slides. So for deployment, right? So we saw different types of machine learning problems, and how, like, for each type, what are the different subtypes and so on, right? So supervised, we saw supervised algorithms, we saw unsupervised algorithms, then we saw semi-supervised, then we even saw reinforcement learning, right? One small example on reinforcement learning, right? So like that we have developed the model, how to basically use it, right? And where to use it, right? So depending on the use case, you would be using the model on different cases, right? And why you would be using that on cloud, right? So that is first thing that I would like to answer first, right? So what happens is, when you are wanting to do it yourself, like cloud helps you do a lot of different things, right? So with just, like, it's not just about deployment, but it helps you with the management of the infrastructure, right? So it goes from VPC, like basically virtual private network, the storage configuration, the serving stack, the ML frameworks, and so on, right? It gives you the capacity of A/B testing different models, canary deployment, updating the endpoint, rollback when the newly updated model was bad, right? Then it has all the security compliances, so it has a list of different certifications which is there, right? It comes with that. Then apart from that, it also gives you logging facility, right? So all the host matrices, response matrices, latency, and everything is basically logged on the cloud itself. The endpoints, once deployed, they are highly available. So it's totally up to you to how much scalable the endpoint be. So endpoints are by default highly available, and as the traffic increases, it is bound to scale, and it is like any bad instance, let's say within a deployed endpoint, would be the cloud takes care of the replacing of that instance and so on. So it also provides cost optimization for multi-model endpoints, like multiple endpoints within the same, on the same, multiple models within the same endpoint, right? So similarly, it also provides multiple containers on the same endpoint. And these are all the small stuff, right? So model handling function, then explainability, lineage tracking, and so on, right? So all of this comes with the cloud. Now, usually the deployment, for any machine learning workload, can be broken into three different types. First would be the real-time inference, then would be the near real-time, and thirdly would be the batch transform. Now, any real-time inference that you'd be wanting to make should have certain should be following a certain specs, right? So it's like it should be giving out the inference latency should be some millisecond to sub-seconds, right? The payload size would be low, but the response time should be less than 60 seconds, and inferences would be synchronous. So any endpoint that you deploy, if it is a real-time endpoint, you would have to follow these particular norms. But let's say your payload size is more than 1 GB, like up to 1 GB, and you are okay with a response time which is up to 15 minutes, then asynchronous inference is something that you would be using, right? In this case, seconds to minutes is the latency. And then finally is the batch transform. So batch transform, what happens is on demand when you want the inference, right, is when the batch transform happens. So let's say you are doing every week, you train a model, and then once the model is trained, you do an inference on the collected data for that particular week, right? So that is something that can be done with batch transform, and it's usually the cheapest. So basically, what I want you to take away from this is, right, this slide is basically that, yeah. So once you develop a model, right, you should be asking questions like, okay, how the model needs to be consumed, right? So depending on that, like how the model would be consumed, depending on that, you would be selecting, okay, how the deployment strategy would be, right? So asking such questions, you would be getting brownie points on, okay, that you basically know your stuff. Now the next steps, right? So apart from this, what else that you should be knowing about, right? So apart from all of this supervised, unsupervised, semi-supervised, reinforcement and deployment strategies which are out there, right? You should be knowing about model monitoring and sharp analysis. Why? First, model monitoring. So model monitoring is okay. So model monitoring using a model metric stack is essential to put a feedback loop. So like once you, so take for an example, once you train a model, build a model, evaluate it, productionize it, testing and deployment, right? So you would have to continuously monitor that model and get a feedback loop to get that model better, right? So that the model keeps on improving under different scenarios, right? So let's say why model monitoring is even important, right? So there is something called covariance shift, where the distribution shifts for each of the independent feature, like the basically the training data, the distribution of the training data, and the production data that is coming, right? So input data has basically changed, and hence the covariance shift can take place, right? So basically the data which is incoming, that distribution changes. So this can happen from a time when, like, COVID, for example, COVID just hit the e-commerce industry, right? So the input data that was coming to the models just changed. So that was particularly the covariance shift. And then there is something called prior probability shift. So what happens is the distribution shifts, the distribution of the predicted output shifts. So there is a shift in the predictions that are coming out. So that is basically like the model performance has basically shifted from the time we trained it on. Okay, so that's called prior probability shift. And then there is something called performance metrics. So performance metrics, as in like performance matrices, are used to detect the shift in concept, right? So what I mean by that is, hello. I think my screen just got disconnected. Let me share my screen again. Okay. Hope the screen is visible again. Okay, so now what happens is like performance matrices can be used to detect the shift in the concept, right? So detecting, basically identifying whether the relationship between the independent and the target variable has changed, right? So post COVID, the way user purchased during festival may have changed, right? So this was the concept shift that happened, right? So they do so by examining good or bad the existing deployed model is whether the existing deployed model is performing good or bad during the previous time frame after the deployment, right? So different matrices that can help you track this performance matrice changes or concept shift is basically like RMSE, R square for RMSE or R square for regression or accuracy, AUC, ROC for classification. Then you also have KS statistics, which are basically the statistical measures to detect on how well the predicted probability classes are separated, right? To help you detect this concept shift. And then there is something called operation matrices. These matrices help us determine how the deployed model is performing from a usage point of time. So as such, independent these matrices are independent of the model, the data, and don't require input from any of the two matrices, right? But it basically takes into account of the throughput that is happening of the machine learning endpoint, basically the number of requests that are hitting it. Then the latency when we call the ML endpoint. So basically the average response time, the memory IO, the CPU usage that is happening, the disk utilization, the system uptime. So all of this. So hence, because if you look at this, all of these are the different reasons why model monitoring is something that you should be knowing about. And then last but not the least, we have SHAP analysis, like model explainability using SHAP. So SHAP stands for Shapely Additive Explanations. SHAP analysis is like one of the most popular model agnostic technique that is used to explain predictions, right? Shapely values are obtained by incorporating concepts from cooperative game theory and local explanation. So it's a bit theoretical, but to put it formally, SHAP values are calculated for each instance and each feature one by one, right? SHAP algorithm basically iterates over each of the instances, and within that instance, it selects a feature and makes all the other features value constant and randomly picks the said feature for which we are calculating the SHAP value. And then basically model predicts the probability to default for this particular simulated situation. And then basically the difference tells us, okay, how the model would be performing for different values for that particular feature, right? When rest of the features are constant, right? So to make it simple to understand, right? So if we look at this particular graph, right? So this is coming from a Titanic data set, right? So where we see that if, let's say, the gender, if it was male, then it has high probability that it would default. Basically, if the sex was male, then it's high probability the outcome, the probability for that particular prediction would be negative, like very small as compared to free female. For female, the probability output would be very high. Similarly, whether if the class belong to high, then the probability for that person to be dying would be high as compared to when the class was low, right? So let us check this out with an Jupyter notebook. Okay, this. So just what I will do is, okay, let me just stop my screen share and reshare it again for the Jupyter notebook. Um, yeah. So in this particular example, what I'm doing is I'll be calculating Shapley values, right? So this is, so I'm using housing data set, right? Whether like this is California housing data set. It talks about what is the population of that area, latitude, longitude, the age of the house, total rooms which are there, total bedrooms, household, the median income, and median house value, right? The target variable in this case is basically the median house value. Now, what we can do is like, yes, we can train the model, but for the sake of it, what we will just skim through it, like because we are wanting to test what Shapley values are, like how it looks like, how we can interpret it, right? So what we do is we just quickly train the model. So for our X, we are using latitude, longitude, housing median age, total rooms, income, household, population, bedroom, and then our target variable would be median house value, right? We create the trust and split and do a random forest regressor. So once this regression is done, we calculate, okay, what is the MSE for our training that is did. That's around like 68,000. So what we do next is basically how to use Shapley values for each of the prediction that is happening. So what happens is for any prediction that takes place, this housing median age equals to 58. This value is basically pushing the base value towards the right? Basically pushing the prediction towards the right. So right now the prediction is at 70,000 $189.83, right? But this median income of the house, the latitude, longitude are pushing this value towards the lowering the value of the house. So that is how you basically interpret the explanation given by Shapley, right? So any questions till this point? I think that was all that I had. Let me check the YouTube. So just coming to the YouTube. Are there any questions which are there? Hello.
Akash is said, sir.
Okay, yeah, Akash. Are there questions in the chat? Like I couldn't see much in the YouTube comment section.
The recent one has been already been placed by Sneha in the chat box of our team.
Okay, I think I have answered them.
Okay.
For now. Just let me go through them once again. Yeah, these questions were answered beforehand, so that's fine. So that's all content that we had for this today's lecture. I understand this would be quite heavy for all of you to hear in one go, and so because we covered a lot of topics, right? So what I would recommend is like you'd be getting GitHub links shortly, like post this, and the recording and everything would be there in YouTube as well, right? So try to emulate the steps on your own. Try to run the notebooks on your own to get this running, to get the feel of on how to do machine learning, right, on your own systems. Yeah. So thank you for being such a kind audience. Yeah. Over to you, Akash.
Yes. Thank you all for joining us for the machine learning workshop. I want to thank our amazing speaker, Mr. Shansa, for this insightful presentation, our dedicated organizing committee, and enthusiastic participants for the contributions. Let us use this knowledge gained on this workshop to advance the field of machine learning and make meaningful contribution to the society. Thank you all the participants. Kindly fill your attendance form in the description mentioned below.